Det är dags för dig att stänga av musiken om du kan göra det. Välkommen till disputation. Welcome to this dissertation defense where Erik Widman will defend his doctoral thesis, Ultrasonic Methods for Quantitative Carotid Plaque Characterization. The opponent is Associate Professor Mark Palmeri from Duke University in Durham, North Carolina, United States. The examination committee will consist of Docent Magnus Sintio from Lund University and Docent Rebecca Hultgren from and Docent Christer Grönlund from Umeå University. The main supervisor is Docent Matilda Larsson, sitting over there. And we also have, I think, present the co-supervisor, Kenneth Kaidal, over there. My name is Örjan Smedby, and I will be the chairman of this part of the dissertation defense in this room. The procedure will be as follows. After announcing potential errata, Erik Widman will himself present both the background and the content of his dissertation. After that, the opponent will have a more or less lengthy critical discussion of the contents of the dissertation, its strengths and weaknesses. After the opponent, it will be the turn of the members of the examination committee to ask their questions. And finally, everyone in the room will be allowed to ask questions to Erik Widman. When this is finished, the examination committee will withdraw, but everyone else is invited to come to the top floor of this building. If you go in that direction and take either the escalator or the stairs, or the elevator or the stairs to the top floor, there will be some refreshments while we're waiting for the decision of the examination committee. And with that, I will hand over to Erik. Please, just do you have any errata?
Yes. Okay. So there are 7 changes to the thesis. The first is on page number 5, line 10. Article number 3 has been accepted for publication. Second, on the same page, line number 13, Article 4 is under review with major revisions. Sure to turn off my own phone. On page 30, line 35, it should be axial motion estimation was only performed on the envelope detected signal. Page 30, line number 9, page 45, line number 5, and page 49, line 33. We have 3 of the same changes. Where should be were. Page 44, figure 9, the group velocities in the figure in figure D, E, and F should be 1.61, 1.58, and 1.77 meters per second, respectively. On page 49, line 20, the sentence, study 1 is an important contribution to the field since it non-invasively focuses on evaluating plaque strain, should be changed to study 1 is an important contribution to the field since it focuses on evaluating plaque strain non-invasively. And on page 54, line 18, 2 millimeters should be changed to 1.5 centimeters.
Thank you. And then I'll give you the word for your own presentation. Please.
Okay. Thank you very much. So this is an exciting presentation for me. We have people from the other side of the world here. We have some people from places closer nearby. I'm equally happy that both of you could come today. And this is kind of a different type of presentation because it's not so common that you have the opportunity to present for such a diverse crowd. We have experts from the field. We have experts in other fields here. And then we have people that don't have a scientific background. So it's going to be my attempt to try to give a high-level presentation so that everyone comes away from here understanding something. And the title of my talk is called Ultrasonic Methods for Quantitative Carotid Plaque Characterization. It's kind of a long, scary title, but I think by the end of this presentation, I think you'll understand what that sentence actually means. So let's dive right into it. So I've always wanted to become a mad scientist. For the past 4 or 5 years, I've been working on the mad scientist hair, and I believe, with your help, that maybe by the end of this presentation, just maybe, I might finally become that mad scientist that I've always aspired to become. So this presentation today is going to have kind of a mad scientist theme to it, if you will. So what I'm going to show today is that quantitative ultrasound methods, that they have the potential to improve current carotid plaque characterization assessments in the clinics. I'm going to present three techniques. The first is called Speckle tracking motion estimation. I'm going to show that it can measure radial and longitudinal plaque strain in vivo. The second technique is called Shear wave elastography. I'm going to show that we can measure the stiffness of simulated plaque in vitro, and it has the potential for in vivo measurements. And third, I'm going to present a third technique called pulse wave imaging, which can also be used for plaque characterization, but it is more sensitive to the plaque thickness, and which might make it more difficult to use in vivo. So these 3 points will make more sense as we go through the presentation. Brief outline. I'm going to give you an introduction to the field. Then I'm going to talk about the aims of my 4 studies. I'm going to talk about the methods, results, and conclusions. Then I'm going to end with giving you my perspectives on the future treatment of cardiovascular diseases. So let's dive in. So what is this all about? Cardiovascular diseases is the #1 killer in the world. About 17 million people annually die from CVDs. The #1 killer in the world is ischemic heart disease, more commonly known as heart attack. Cerebrovascular disease, also known as stroke, is the second killer. And that's what we're going to focus on today. So there are 5 key risk factors for cardiovascular diseases. They are smoking, alcohol consumption, physical inactivity, unhealthy or poor diet, and genetic disposition. So this is my favorite slide of the presentation, so just kind of take this one in and enjoy it. So, like I mentioned, due to these 5 risk factors, we can develop plaques in our arteries as we age. We can develop them in our coronary arteries, or we can develop them throughout our arterial tree. It's fairly common to develop them in the carotid arteries near the bifurcation seen here. And this is a very slow progressing disease. It takes 20 to 30 years to develop plaques. And it's really, if we kind of simplify the process, it comes down to an increased amount of fats in your blood that you're not able to effectively remove. This causes an infection in the arterial wall, and over time, this can kind of build up with dead and fatty tissue, and over time it can become what we call a vulnerable plaque. So this plaque is dangerous, and there are 3 outcomes if it does. They are thrombotic stroke, embolic stroke, and cerebral hemorrhage. Thrombotic stroke occurs when a blood clot or a thrombus develops in your arteries, which blocks the flow of blood, limiting the oxygen supply to your brain. Embolic stroke happens when an embolism breaks off, or part of the plaque breaks off, travels further down the circulatory system to narrower blood vessels, also limiting the blood flow and oxygen supply to the brain. And third, the cerebral hemorrhage occurs when the artery tears, or we have an aneurysm, which causes a bleeding in the brain, which can also be fatal. There are many different types of plaque, but we often kind of put them into 2 categories, stable and vulnerable plaques. Here we see a cross-section of the carotid artery. So this is a normal carotid artery. It consists of 3 layers. The outer layer is the adventitia, the middle layer is the media, the inner layer is called the intima. And this is the lumen. That's where the blood is flowing. So a stable plaque, they typically have a small lipid or necrotic core and a lot of calcified material or fibrous material around them. Vulnerable plaques typically have a large lipid core and a thin fibrous cap, which makes them more likely to rupture, causing stroke. So to simplify or to illustrate this, I'm going to talk a lot about stable plaques and vulnerable plaques throughout the presentation. You can think of stable plaques as hard, like a brick wall. They're not going to go anywhere. And vulnerable plaques are like a big pile of mush, so they can break and cause stroke. So think about the mushy dog here when I name vulnerable plaques. There are also many different types of vulnerable plaques. They can have different composition, necrotic or lipid fatty cores. They can have neovascularization. They can have intraplaque hemorrhage. And it's important to keep in mind that this makes it even more difficult to identify which ones are vulnerable and try to figure out which ones are going to rupture to cause stroke for the patient. But how is the patient diagnosed today? The patient goes into the clinic, they meet the doctor, and they undergo what we call a ultrasound duplex scanning. What this is they take a picture of the carotid artery, and they look for plaques in the artery, and they also look at the blood flow. And they're looking for a couple different things, partially the morphology of the plaque, how much echo or how much echo is bouncing back from the plaque from the ultrasound. But primarily what they look for is the size of the plaque, which is often called the degree of stenosis. If the degree of stenosis is greater than 70%, then they operate on the patient. They perform an endarterectomy, they remove it, or they can perform an angioplasty, meaning they place a stent in the artery to widen it, to increase the blood flow. So, but you can also do things like medicate the patient with blood thinners, or you can prescribe healthier diet or exercise. Now, sometimes it's more risky to operate on a patient. There's always risk involved with surgery. Sometimes you don't want to do anything. So that's why we want to try to detect the stable plaques from the vulnerable plaques to prescribe the best treatment for the patient. So today this is visual assessment of the size of the plaque, assessing the size of the plaque, but several studies have shown that visual assessment is not a good technique for determining plaque vulnerability. And this makes sense, right? Just looking at a plaque, we don't know anything about its mechanical properties. So that's why we're trying to develop these quantitative techniques to put a number on the likelihood for plaque rupture. And that's what I've been working on the past couple of years. So the general aim is to develop ultrasound techniques that quantitatively characterize the mechanical composition of the plaques to assess stroke. So physicians can better determine what kind of treatment they're going to give their patients. And we've been working on 3 techniques: speckle tracking, motion estimation, shear wave elastography, and pulse wave imaging. So that's what I'm going to cover today. In study number 1, we focused on speckle tracking. Studies 2, 3, and 4, we talked about shear wave elastography. And in study 4, we compared pulse wave imaging to shear wave elastography. So with that, let's go ahead with study number 1. That's right. Where we're going, we don't need roads. This is our first mad scientist. This is Doc from Back to the Future. He's going to bring us to our first study. And here we're going to use speckle tracking, like I mentioned. So let's talk about what speckle tracking is. You can basically think of it as motion estimation. A video sequence consists of a group of images, and an image consists of a bunch of pixels, right? So we can track a group of pixels from frame to frame and detect motion. So I'm going to illustrate this here. So we track what we call the kernel, which is nothing but a group of pixels. We have our first frame here. We compare it to the next frame, search for that group of pixels within a search area, and then we can track the motion of that group of pixels. We can do that over a series of pictures and track the motion throughout a cardiac cycle. And our hypothesis is that vulnerable or soft plaques should have greater motion than hard or stable plaques, which should exhibit less motion or strain. So here's an example of this. And I'll try to make the room just a little darker so to make it easier to see the videos. So we have 2 patients here. We have a 72-year-old female. We have a echogenic plaque in the posterior internal carotid artery wall. These plaques tend to be more stable. We have echolucent plaque, which tends to be more vulnerable, right here in the posterior wall of this common carotid artery of this male patient. And we can measure the motion in the radial direction. The radial direction will be the up and down motion here throughout a cardiac cycle. And what we see is that we have twice as much radial strain or radial motion in the echolucent plaque compared to the echogenic plaque. So that's the whole idea, to look at how much the plaque is moving throughout the cardiac cycle to try to identify which ones are soft and which ones are hard. Okay, So in the first study, we have the speckle tracking algorithm, and we're going to try to validate it against another technique called sonomicrometry. We're going to then, once we validated it in a phantom setup, we're going to do a small in vivo pilot study on a couple of patients and see if we can measure plaque strain in vivo. So we made these phantoms, these kind of like simulations of the carotid artery, and they have plaque inclusions in them, a simulated plaque on the inside of them. This is a cross-sectional schematic of the phantom. This area right here becomes the plaque, and we glue 3 of these sonomicrometry crystals to it. These crystals, they can measure distance from each other. So they can measure the motion in this direction, the longitudinal direction, and in the radial direction, which will be up and down. You can see these green wires coming off the phantom. These are the crystals that we have glued to the phantom. So we surround the phantom with agar to mimic the tissue and the throat. We then fix our ultrasound probe above it, and we connect this to a pump to mimic the heart cycle. We can collect our ultrasound data, and then we can collect our sonomicrometry data and compare the two. And this is a screenshot from our data acquisition. So this is our region of interest. This is where we track the motion with our speckle tracking algorithm. This is the plaque. Here you can see the sonomicrometry crystal glued to the inside of the lumen, and there are 2 on the outside right there. So we're going to measure 2 types of motion, radial motion up and down, longitudinal motion to the left and right. Here's a video sequence of what it looks like. You can see that there's quite a bit of motion, particularly in the radial direction, much more than in the longitudinal direction for the plaque. So if we track this with our speckle tracking algorithm, which you see in red, and we see the sonomicrometry system in blue, you see that we have very good agreement between the 2 systems. We have a very high correlation coefficient of 0.96. And we have quite a bit of strain or motion in the radial direction, up to 10%. In the longitudinal direction, we also get fairly good agreement between the 2 systems. We have a little lower correlation of 0.75. Most of the error occurs in the relaxation phase or the diastolic phase of the cardiac cycle. But overall, it looks like we can track both radial and longitudinal motion. So, because we got good agreement, we said, okay, let's go ahead, let's do a small patient study. So we got 7 patients, mean age of 77. We gathered data both in the left and right carotid arteries. And we did our speckle tracking motion estimation. And we also had experienced physicians visually score these plaques on what we call the gray wheel scale. This is a scale from 1 to 4, where scores 1 and 2 correspond to echolucent plaques, which tend to be more vulnerable or more soft. Scores 3 and 4 tend to be more stable or echogenic. So the physicians outlined the plaques, and we could place our search area or our region of interest on the plaque and track the motion. And the results show both in the radial and the longitudinal directions that we have increased plaque strain for plaques scored 1 and 2, the more soft vulnerable plaques, than the plaques that was scored 3, which is the echogenic or more stable plaque. So it looks like our algorithm can detect and distinguish the soft plaques from the more stable vulnerable plaques. So in conclusion, we validated our algorithm with sonomicrometry. We found a strong correlation in the radial direction, a fairly strong one in the longitudinal direction, and we also did an in vivo study and saw that we could distinguish echolucent or more vulnerable plaques to an echogenic plaque. All right, mad scientist number 2. I don't know if you noticed, if you guys were paying attention, but I was trying to find a mad scientist laugh, you know, one of those, but I had to settle for a Scooby-Doo laugh. So I couldn't quite find what I was looking for. But this brings us to study number 2. Now we're going to look at a different technique with kind of the same objective. We're going to use a technique called shear wave elastography to try to measure the stiffness of plaques, and we're going to validate this with mechanical testing. So first, let me talk about what shear wave elastography is. So imagine you're standing by a lake, you have a rock in your hand, and you throw it in the water. The water plunges into the water, and waves ripple across the surface. You can think of these waves as shear waves. So we're going to do the same thing with ultrasound. We're going to use what we call an acoustic radiation force. We often call it a push, and push our tissue like this. When we create this push, waves ripple out through the tissue. Shear waves propagate orthogonally or to the sides of our push, And we can track the motion of these waves using what we call plane wave imaging, which is high-speed imaging. And I have a video of this. We do our ultrasonic push here. The waves travel off to the sides in the tissue. If we know the density of the tissue and we can measure the speed of the waves, we can calculate the shear modulus, which is a metric for how stiff the tissue is. So we're going to try to do this in the arterial wall and in the carotid artery, simulated carotid artery plaques. So we have two objectives. We're going to try to validate this technique with mechanical testing. Hopefully we get the same results. We're going to do this in a motionless, static environment. Once we've accomplished that, we're going to do it in a dynamic environment with motion. So we had two types of plaques. Once again, we're doing these phantoms that mimic the carotid artery. We have soft plaques here, and we have one with a hard plaque here. So we made 3 of each phantom, and we connected them to a fixture, filled the phantom with water, and surrounded it by water, and fixed the probe above it. We could then gather our ultrasound data, and this is what a screenshot from the data acquisition. So these 3 red X's, these are our pushes, and the shear wave propagates off to the left and the right in the plaque, and we measure the speed of the wave between these 2 white lines, okay? So we're going to measure 2 types of speeds, or 2 types of velocities. One's called group velocity, which you can think of kind of an average speed for the wave. The other is called phase velocity. So because of the geometry of the arterial wall and the plaque, we're going to get a lot of reflections for this wave as it travels in the left and right directions. It's going to bounce back and forth, and these reflections are going to cause superposition and cancellation of the wave. This results in a phenomenon that we call dispersion, meaning that different frequencies of the wave are traveling at different speeds. So we have a technique called phase velocity analysis, which allows us to measure the speed of each individual frequency of the wave. So the slide's going to get a little technical, and I apologize in advance for it, but bear with me here. We gather our ultrasound data, we generate a B-mode image, and we track it with a 2D autocorrelator algorithm and get what we call our axial displacement maps. So here we have time and on the y-axis and distance on the x-axis, and the blue line is our shear wave that's propagating through our plaque. We want to then look at the frequencies of this wave, so we do what we call a 2D Fourier transform, which takes us to the frequency domain. We have frequency on the x-axis, the wave number on the y-axis. We can then use another equation where the speed of the wave is equal to the wavelength times the frequency to go to what we call the phase velocity map. And we're interested in the maximum intensity of this plot. And if we crop away these extremities here, these discontinuities, we're left with this dispersion curve. So here we see the velocity of each individual frequency. You can see that they all have a different velocity here. So now we're going to use a model of a wave traveling through a plate and fit it to our data set here. And from that model, we can calculate the shear modulus, which was the stiffness of the plaque. So this is a little complicated, but I hope that you followed me here. So we're going to do 2 types of data fits. We're going to do one on the full bandwidth, and we're going to do one on the upper half bandwidth, which is the upper frequencies of our data set. We do this because ideally we want a model of a wave traveling through a cylindrical geometry. This is a very complicated equation that we haven't solved yet, so we use this easier model of a wave traveling through a plate, and those 2 models, they converge. They're very similar at higher frequencies, so we can use that as a substitute, basically, and get better results. Okay, so we calculated the stiffness with our shear wave algorithm. Now we're going to compare it to mechanical testing. This is a machine where we just place our phantom in the machine and we pull it in the y direction like this, and we can measure the displacement, the distance that we're pulling it, and the force that we're using, so we can measure the stiffness of the material. We're going to compare the 2. So these are the results for our shear wave measurements. We have the soft plaque, hard plaque, and phantom wall. These are our displacement plots, and the lines are the shear wave traveling through the plaque. So this is time versus distance. So this is the speed of the wave. So the slope of the wave indicates the speed that it's traveling at. And you can notice that the hard plaque is traveling much faster than the soft plaque, and the phantom wall is somewhere in between the 2. So if we average the results for all our data acquisitions, and we're looking at the soft plaque phantom in the left, the hard plaque phantom in the right. Red and blue are the left and right shear waves respectively. Green is the mechanical testing. We see that we get very good agreement both in the plaque and the wall in both types of phantoms. So it looks like we get very good agreement with mechanical testing, but remember this was in a static environment, and in the body everything is moving. So we got to do another test. We're going to connect this to a pump to mimic a heart cycle and see if we can do the same measurement again. So we connected it to this pump, which mimics the heart, and this is the flow profile through the carotid artery. And we're going to try to do 8 data acquisitions throughout a simulated cardiac cycle. This is a video sequence of this, and you can see there's quite a bit of movement especially in the soft plaque. But most of this movement consists of low frequencies, so we can actually use a filter to get rid of this movement. We can use a high-pass filter. So if we do that and plot the results, we see that the stiffness varies throughout the cardiac cycle and that it mimics the flow profile curve fairly well for the soft and hard plaque. So it looks like we can measure in a dynamic environment as well. So the conclusions of this study was that we could measure the stiffness in phantom plaques and in the wall, and we validated the results with mechanical testing and got good agreement. We were also able to measure the shear modulus in a dynamic environment and not only in a stable one. It is alive! So, Young Einstein. This is a movie that inspired me as a kid to become this mad scientist that I might become today. He brings us to study number 3, where we use shear wave elastography once again, and this time we're going to try to measure the stiffness of real arteries with simulated plaques. So we're going to do this in pigs. We got pig aortas, used them as a model for the human carotid artery, and we're also going to try to optimize our shear wave algorithm with respect to a couple different parameters. So we got 5 pig aortas, and we cut them to a length of about 10 centimeters. We glued the arterioles coming off the top of it here shut, and we then lowered half of it into a vial of formalin to stiffen it to create a simulated calcified plaque. We then attached it to a fixture with a pressure sensor and submerged it in a water bath, fixed the probe above it, and we connected it to a water column so we could vary the pressure in this artery. Now, we did 4 experiments. The first one, we're interested in studying the bandwidth of the shear wave. We want to look at how many frequencies we have, and we're going to try to vary the push length. The push length is very related to the amount of frequency content that you have in your propagating wave. Why do we want to do this? Remember in the last study that we did this data fit. We had our model that we fit to our data set. So if we can maximize the amount of frequencies that we have, we can increase the amount of data points, and we should get better curve fits. So that's our goal. So we varied the push length from 100 to 700 microseconds, and we measured the maximum bandwidth of the shear wave. We did this at 2 pressures, 60 and 120 millimeters mercury, to mimic systolic and diastolic pressures. If we plot the results, we're looking at the bandwidth or the frequency content of our propagating shear wave versus our push length. We can see that the frequencies drop off as the push length increases, especially around 300 to 400 microseconds here. If we plot these results, we can see that it's fairly consistent until we reach that 300 or 400 microseconds. Then our estimates really take off. So if we go back to the first plot, this means that we need a bandwidth of approximately 1500 hertz in our propagating shear wave to achieve consistent shear modulus estimates with our phase velocity technique. In the second experiment, we wanted to study the effect of the number of imaging angles that you use and our frame rate on our bandwidth of our shear wave. So we're going to use this technique called compounded imaging. And the idea is that you can take a picture straight on, and you can take a picture from 2 or more different angles, add these images together, and enhance your resolution. The downside with this technique is that your frame rate is going to go down. So when we image with 1 imaging angle, we have a frame rate of around 10,000 frames per second. If we use 3 imaging angles, frame rate around 3,000 frames per second. If you use 5 imaging angles, our frame rate's around 2,000. So it decreases rapidly. And we're going to use a fixed push length of 100 microseconds, do it at 2 pressures once again, 60 and 120 millimeters mercury, and measure the bandwidth in the wall and the simulated plaque. So if we look at the results, we have the imaging angles on the x-axis, the bandwidth on the y-axis. We get a large bandwidth for one imaging angle, and you can see that the bandwidth decreases rapidly at 3 and 5 imaging angles. And in many cases, it's so low that we can't even measure the bandwidth for the Shear wave. And this is at 60 millimeters mercury in the wall and plaque, and 120 millimeters mercury in the wall and plaque as well. So it looks like the conclusion that we can draw is that it's more important to have a lower image resolution, but have a really fast frame rate in order to achieve a large bandwidth, which will give us the best phase velocity estimates. The third experiment we did, we wanted to study, see if we could measure the stiffness in the wall and the plaque as we increase the pressure. We varied the pressure from 20 to 120 millimeters mercury in increments of 20 millimeters mercury. We had a fixed push length of 100 microseconds. If we plot the results for the wall, and we have pressure on the y-axis, stiffness or the shear modulus on the x-axis, on the y-axis, we have our 5 arteries labeled A1 through A5. We can see that the pressure increases as we increase the pressure. And in the simulated plaque, the shear modulus estimates increase as well. And it's worth noting that the shear modulus estimates in the plaque are much larger than the wall, of course. What else is interesting about this plot is between 60 to 120 millimeters mercury, the in vivo pressures, that the increase in stiffness is fairly linear in both the plaque and the wall. And we think this is a byproduct of our experimental setup. Because remember, we're increasing the pressure, we let everything kind of rest, and then we do our measurement. In the body, that's a dynamic environment. The pressure increases and drops off very rapidly, and they expect a nonlinear response in the tissue. So for the final test, we did a sensitivity test. We wanted to see how sensitive our algorithm is to small changes in stiffness. So we took one artery, we had a push length of 100 microseconds, did this experiment at 60 millimeters mercury, estimated the shear modulus in the plaque with respect to the soaking time. So we have our time here on the y-axis from 0 to 10 minutes, and you can see that we can detect very small changes in increased stiffness in the plaque. And this suggests that our algorithm could potentially be used for diseases like arteriosclerosis or stiffening of the arteries to measure and monitor that disease over time. So, in conclusion, study 3 found that a short push length of 100 microseconds resulted in the largest bandwidth, and that we need a minimum bandwidth of approximately 1500 hertz to obtain consistent shear modulus estimates. Moreover, we found that a high imaging frame rate is more important than a lower frame rate with better imaging quality. Okay, so this is Professor Fink from The Simpsons, our final mad scientist for today, and he brings us to study number 4. And now we're going to compare shear wave elastography, which I've been talking about, to a new technique called pulse wave imaging. And I'll go over that technique right now. So pulse wave imaging is an ultrasound-based technique that's based on a clinical technique called pulse wave velocity. Every time our heart beats, a pulse wave is generated from ventricular ejection. It travels throughout our arterial tree and dissipates. And the speed of this wave is correlated with the stiffness of your arteries. So if you have very stiff arteries, the wave travels quickly. If you have healthy arteries, the wave travels slower. So in clinics, they place 2 sensors, one by the carotid artery and one by the femoral artery. And they measure the time it takes for this pulse wave from the heart to travel between these 2 measuring points. So then we can measure the distance, we know the time. From that, we can calculate the pulse wave velocity. Now we can do the same thing with ultrasound. So we can grab an image of the carotid artery using our high-speed plane wave imaging, and then we can measure the pulse wave as it travels through our carotid artery. We can measure the speed of this wave, This is actually displacement that we're measuring in red and blue there. And the speed of that wave corresponds to your arterial health, the arterial stiffness. So we're going to do this in the wall, and we're going to do this in plaques in a phantom setup. So the goal is to compare these two techniques, and once again, we're using these phantoms with the plaque in the anterior wall. And we connected this to a fixture. We did 3 phantoms, connected them to the fixture, filled it with gelatin, fixed our ultrasound probe above it. We connected 2 tubes to the inlet and outlet and filled it with water to 20 millimeters of mercury pressure. We then could gather our shear wave data first. Then we would pinch the tube, which generates a pulse wave, which travels through the wall, then through the plaque. And we measured the speed of this traveling wave to compare the velocities of both the shear waves and the pulse waves. And here we see the results for the 3 plaques. So the first important thing to notice is that they're all different thickness. Plaque number 1 is the thickest at about 6.7 millimeters. This one is 2.7 millimeters. The red line, that's where we track our pulse wave. The yellow dashed line, that's the area where we're comparing the 2 different techniques. First, we're going to take a look at shear wave elastography. We have our group velocities here from our axial displacement maps. They're fairly consistent. We have our phase velocity, our curve fits here in the second row. They're also fairly consistent. Now what's interesting here is to compare this to the pulse wave results. So these are axial displacement maps for the pulse wave. We measure this first wave here that travels through the plaque. All this red stuff, this is reflections for the pulse wave as it bounces back and forth in the fixture. But we're only measuring the speed of the wave on this first wave that travels through the plaque. If we do a linear fit on our data points, we can estimate the pulse wave. But notice that we have a much smaller pulse wave in the first plaque compared to the third plaque. And the only difference is they're the same stiffness. The only difference is the thickness of the plaque. So this means that the pulse wave is more sensitive to plaque thickness compared to shear wave elastography. This becomes more evident if we average the results and plot them. We have the wall here to the left, the plaque to the right. If we compare the phase velocity and the group velocity in blue and orange compared to the pulse velocity in gray, we can all see that those wave speeds are fairly consistent. But notice that in the plaque, as the plaque thickness changes, that the pulse wave velocity takes off while the group and phase velocities are consistent. So that reiterates that pulse wave velocity is more sensitive to plaque thickness than shear wave elastography. One other note, we're comparing 2 different types of waves here, pulse waves versus shear waves, and it's not really expected that we should get the same wave velocity. This is more due to, it's kind of by random chance that we have the correct ratio of the wall thickness to the diameter of our plaque, or wall in this case for our phantoms, which influences the pulse wave velocity. So in conclusion, we showed that we can measure the stiffness in the wall and in the plaque with both of these techniques, but pulse wave velocity appears to be more sensitive to plaque thickness than shear wave elastography. However, pulse wave imaging has other benefits. It can examine a larger area of the plaque, and it also tracks a stronger wave. The pulse wave is much stronger than the shear wave traveling through the arteries. Okay, back to this slide. So now this slide makes a little more sense, right? So what I've shown here today is that these quantitative ultrasound-based techniques, that they can help physicians in their current assessment of plaques to better diagnose patients that are at high risk for stroke. I showed that speckle tracking, that it can measure both radial and longitudinal plaque movement or plaque strain in vivo. We can measure the stiffness of plaques using shear wave elastography in vitro, and has the potential for in vivo measurements. We could also measure stiffness with pulse wave imaging, but it appears to be more sensitive to the plaque thickness, which might make it difficult for in vivo characterization. Okay, so now I'm going to end my talk talking about the future of cardiovascular diseases. So this is a value chain for healthcare, prevention, diagnostics, and treatment. I've been talking about this area so far today. And most of my career, I've either been working in diagnostics or on the treatment side of various diseases. But what I've found, the more I work in healthcare and in medtech, I found that we spend too much time and effort on coming up with very complex solutions to diseases when we should be focusing on preventive medicine. And that's what I'm going to be talking about now. How do we use preventive medicine to significantly reduce morbidity and mortality rates for CVDs? So there are 5 key areas that we need to focus on. They are personal responsibility, access to healthy dietary options, support from the government, support from employers, and changing social norms. So let's start at the top. Of course, all of us have a personal responsibility to take care of our own health, but it's not as easy as just saying, hey, go eat healthy, go work out. The truth is that all of us come from different socioeconomic backgrounds. We've been dealt different cards in life, and it's just not possible, either through our jobs or through whatever our life situation is, to live a healthy lifestyle. And that's why we need these other 4 areas to make it easier to live a healthy lifestyle. So first, we need to provide access to healthy dietary options, and we should really target low-income socioeconomic areas. We have data that shows that these areas in Sweden have the highest mortality rates for CVDs, the highest incidences of CVDs, and that they also have a shorter life expectancy than wealthier parts of Sweden. So we need to provide healthy options in grocery stores in these areas. This can also be done with the support from government. I'm going to talk more about this in the next slide, so I'm going to skip to support from employers. It's important to think about what's been happening throughout the world the past 30, 40, 50 years. We used to have jobs where we worked in a factory, we were much more mobile, and nowadays most of us, here in Sweden at least, sit in front of a computer and type away all day, and there's not a whole lot of movement. If you wear a step counter and count how many steps you actually walk per day, if you have an office job, it's almost shocking how few steps we walk. It can be under 1,000 steps per day, which is very little. So we need to rethink the way we're working. We need to rethink the way the future jobs are going to look. Employers, we need to change our working culture, our working lifestyle, so that we can exercise and work out during our work hours, include breaks for that. We also need to make sure that we have healthy dietary options in the workspace. Not only is this going to give us added health benefits, but it's going to add to productivity and make the workers feel better. The 5th area that we need to think about is changing norms. This includes peer pressure when it comes to things like smoking and alcohol consumption, of course, which are bad for you. But it also comes to lifestyle choices. I think particularly here in Sweden, we do what I call follow the herd. We're afraid to stick out from the mass. It's kind of embedded in our culture to a certain degree. And from as small of things as having fika every day. Why do we have fika? It's mostly a social thing, right? So we have to allow people to be different, to eat different, encourage them to do that, encourage them to exercise, and be maybe more open-minded than we have been traditionally in Sweden. Okay, so I think this is great. I can pat myself on the back. I've pointed out some great points here, how to improve healthcare and reduce cardiovascular diseases in Sweden, but this doesn't really mean anything if we don't try to quantify it and put some numbers on it. And that's what I've done. So I got some data from the Heart and Lung Foundation and Socialstyrelsens database to try to quantify the economic effect of reducing cardiovascular diseases in Sweden. So we have about 1.5 million Swedes that suffer from CVDs. We have 30,000 stroke patients annually. We have almost the equal amount of myocardial infarction patients. The total treatment cost for these 2 groups is about 11 billion crowns. The total treatment for CVDs in Sweden annually is 62 billion crowns. Now, I believe with a variety of changes, we can reduce CVDs up to 25%. If we can reduce it by 25%, this will result in 16 billion crowns in annual healthcare savings. So if we assume perpetuity on this, that it's going to go forever, and that we have an inflation rate of 2%, that means that we have a present value savings of 800 billion crowns, almost 1 trillion crowns in cardiovascular disease savings by implementing a variety of changes. Now, this is just savings for CVDs. This is also going to affect many other diseases like cancer, for instance, and diabetes. So the healthcare savings are in reality even greater. So what can the government do to lower cardiovascular disease rates? I think there are 6 things that we can do here in Sweden to get the morbidity rates down. The first thing we need to do is to subsidize healthy food at the same time as we impose a sugar tax on sugary food. This might sound kind of extreme to some people, but this is actually already being done in different parts of the world. Mexico, for instance, they have the most obese population in the world. They have a problem with diabetes there. And they've recently imposed a sugar tax which has reduced the amount of soda consumption, and it's going to result in millions, if not billions, in healthcare savings in that country. We need to do the same kind of thing here in Sweden. We need to talk about subsidizing gym memberships, particularly in low-income areas. One benefit that we have in Sweden is that we have a really good infrastructure with exercise facilities, and this has been built up over time. However, not everyone has the financial ability to attend these gyms, but I think we need to assist low-income people in doing so. Like I said, we should get the low-income socioeconomic group that has the highest CVD rates. The other thing we need to focus on is education. So we currently educate our students in grade school about health and exercise, and that's great. But I don't know about you, but I've forgotten most of what I learned in grade school, and that's why we need continuous education throughout our adult lives. We need national marketing campaigns that remind us how to eat healthy, how to exercise, and why to do it. What effect does it have on our health and our well-being, our productivity, and correlate that to a variety of diseases. The sixth and final thing we should do is use technology to reduce cardiovascular disease rates. Things like Fitbits, mobile apps to remind us to eat healthy, to work out, to be mobile, to monitor what we're doing, to also remind us to go to bed in time, because sleep is very important to reduce our stress rates, which affect our cardiovascular diseases as well. So these are 6 things that the government can do to effectively reduce cardiovascular disease rates and save a lot of money for our healthcare system. What can you do to improve your own cardiovascular health? There are 4 key things that you can do. I've listed them in order of importance. The first one is to avoid tobacco use. It's obvious to most people. Tobacco causes cancer, but a lot of people don't know it also causes cardiovascular diseases. What's more difficult is to avoid secondhand smoke. Secondhand smoke also causes cancer. It's just like smoking a cigarette yourself. So if someone's smoking next to you in a public place, tell them to stop smoking. It's okay to be that person and tell them that it's not okay to smoke in public. Limit your alcohol consumption. The American Heart Association recommends 1 to 2 drinks per day for men if you're going to drink, 1 drink for women. If you're serious about health, don't drink at all if you want added benefits. That would be my recommendation. They also recommend that you should exercise for 30 minutes, 5 days a week. And there's 2 things I want to point out here. The first is exercise comes in a lot of different varieties and forms. It can be as simple as taking a walk. It can be dancing. The important thing is that you just do whatever you think is fun. And if you do that, then it won't feel like you're working out. So just keep varying it up, keep the body guessing, and have fun with it. The second thing is you're not exercising today. It's really easy to get started. It can be as simple as taking a 30-minute walk each day. What should this walk look like? Well, try to walk in intervals. So walk 25% faster than you normally do for 3 minutes, walk 25% slower than you normally do for 3 minutes, and you'll get added benefits versus walking at a constant speed. Now, if you want additional health benefits, 2 of these exercise sessions should be for 45 minutes and involve strenuous muscle activity. And finally, you should eat a Mediterranean diet. The Mediterranean diet is kind of universally considered by physicians the most healthy diet for cardiovascular diseases. And I'm going to go over it right now. So most of your diet should be down here on the bottom layer. It should consist of fruits, vegetables, greens, beans, olive oils, nuts. Basically, you can kind of summarize it this way. Growing on a bush or from a tree, or coming from the ground, from nature, as long as it's not poisonous for us, it's generally considered healthy, right? Our meat should consist primarily of seafood, and we should be drinking water. If we go up a level, we should be eating white meats like chicken or turkey. And at the top, we have our meats and sweets. In Sweden, we have a guideline that you should eat a maximum of 500 grams of red meat per day per person. not, try switching out the red meat to chicken, for instance, when you're cooking, and I guarantee that you'll feel a lot better from it. If you're going to drink alcohol, drink red wine. Don't drink beer or liquor. So that's what I wanted to say about preventative medicine, and it's very important, so I hope that all of you take that with you. Now, I've been talking up here for quite a while, and I'd like to thank some people. This is obviously a very large body of work, and it's definitely not just my work. It's largely due to this group of people that have helped me in the process. So I want to thank my advisor, Matilda, who's been absolutely fantastic the couple of years, my lab partner and partner in crime, Elira, who challenges me all the time and makes me better at what I do. David and Tim are two other great PhDs on our team. Malin's another great PhD that we have here that I've been working with. Peter Arfet is kind of our unsung hero in the lab. He's one of the best lab technicians in the world. He makes experiments that many large universities cannot even do. They can't even do these experiments that we've been doing the past couple of years, and that's largely due to his skill, his craftsmanship. So he's a valuable asset for the school. Kenneth has taught me so much about medicine the past couple of years and atherosclerosis, and it's been very fun learning about that. I want to thank our partners at the Mayo Clinic, Columbia, and KU Leuven, our groups there, and thank my sources of funding, including the Royal Academy of Sciences, Royal Academy of Engineering Sciences, and the Heart and Lung Foundation. All right, it's time for some questions. Thank you very much.
Thank you, Erik. And with that, I'll hand over the word to Mark Palmeri for the critical discussion, please.
Great. Well, thank you very much. I'm Mark Palmeri from Duke University. I wanted to first thank Erik and Matilda for identifying me to be part of this process. I think defending a thesis is one of the most exciting times in someone's career, and as Erik has shown in about the past hour, a very comprehensive project here. Can sometimes be unsatisfying in a presentation. You've summarized 5 years of work in less than an hour, and so I counted about 60 scientific slides, so about each slide took a month of work to put together. So
Sounds about right.
So, my hope here in this questioning really is actually to start to peel apart the onion a little bit and let Erik actually expose some of more of the detail of what's gone into such a comprehensive project here. I was going to start off with a few generalized questions and then kind of go through each of the 4 studies in a little more detail there. As you mentioned, you described 3 major topics of technique to characterize mechanical properties. One of my big overarching questions for you, kind of now having taken in all of this work, is you right now have presented singleton numbers to kind of characterize what could be a very complex architecture of what these plaques look like. Do you think that's a accurate and worthwhile diagnostic way to come up with a single measurement for a complex cap, lipid core, and the sort? And of the 3 methods you presented, which do you think actually has the most clinical traction?
Right, good question. So I think you have to kind of zoom out and look at what the ultimate goal is. The ultimate goal is to develop tools for physicians to better assess which plaques are vulnerable. And I think physicians, we have to think about the information that they want, because I think that's different from the information that us scientists want. We obviously want to know the exact composition of the plaque and all the different stiffnesses in all the different regions. That might not be valuable information for the physician, I think. It might be okay to kind of, many of these techniques, like you said, kind of average out a stiffness for the entire plaque. And that might be appropriate. But I think many of these techniques need clinical studies to validate on a wide variety of different types of plaques if it is okay to kind of average out the stiffness of the entire plaque. So that's the answer to my first part. The second part, which technique has the most clinical potential? That's, I think, either speckle tracking or shear wave elastography have the highest potential for different reasons. I think shear wave elastography is maybe a little closer to real-world implementation, if we stick with something like a group velocity estimate rather than a phase velocity-based estimate, I think speckle tracking, it's already being used to an extent. Some other groups are trying to characterize plaques with it as well, so I think there's a strong interest there as well. But I feel like there's a little more difficulty with that technique, in my opinion.
Going down that path, I think I'll jump right in then to some of the specific studies. So in the first study, you're looking at, as you presented on one of your slides, very large-scale deformation. Those kernels that you're tracking are large in size. From your scientific opinion, how does large-scale deformation of what speckle tracking is sensitive to correlate to more of the infinitesimal strains that shear wave elastography is more sensitive to? Are those comparable, or are they actually looking at different scale mechanical properties of these plaques?
That's a good question. It depends if we're looking at, I think they're looking at different scale mechanical properties, because both group velocity and phase velocity to an extent average either a wave speed, well, both wave speeds actually in the plaque for the entire plaque. I think the difficulty with speckle tracking, as you reduce the kernel size, it becomes more sensitive to noise. It has a harder time tracking the kernel over time. The problem is if we make a too large kernel, it's difficult to move it within the plaque due to size constraints of the search area and the kernel.
What if that kernel is spanning partially lipid necrotic core and partially fibrous cap? How will that influence your ability to get an accurate single deformation?
Right, so that we had examples of that in vivo where most of the plaques were a mixture of echogenic and echolucent plaques. In reality, most plaques are of mixed composition. They aren't just lipid core or just stable, but most of them are a mixture. So in our study, we tried to place the kernel between the two regions and kind of take an average, if you will, of both echogenic and echolucent regions in the plaque. I think that's one way to try to overcome it.
Great. Getting more into the kind of minutia of how you actually do the displacement estimation, and I'm highlighting this back to the actual paper itself. Page 80 of the paper mentions you kind of use two interpolant methods to actually go through the process here, that you use a spline-based interpolant to get subpixel motion estimation, and then you use a linear interpolant to actually accumulate the displacements. So I was wondering if you could describe a little bit what the spline interpolant is doing to get the initial sub-incremental resolution there, and then why switch to a linear interpolant to do the accumulated?
Sure. So I'm going to try to draw this and illustrate it. I think that's the easiest technique here. So let's see. So I'm going to draw two frames here. So we have our grid of pixels. And I'm kind of going to simplify it a little bit. Say we just want to track this pixel from frame t to t+1, our next frame. Say, well actually we'll consider that this is a group of pixels, but say that group of pixels falls somewhere like that in between these different search areas. So then what we're doing is normalized cross correlation. And we might get something like in this first region, we get a normalized cross correlation that's right there. More of the kernels in that one, so we get a higher normalized cross correlation there. We get a little less than that one, and we'll just say that last one's right there. So then we can do a spline interpolation between these three data points or so, and say that if we say that spline interpolation, there was a peak right there, that would be our normalized cross correlation for that kernel movement. So in that sense, we have subsample resolution. Now, in terms of the linear estimation, we can move our searchable area. I'm going to switch colors here. So this is our first search area. We have some overlap. That's our second one. We have a, let's see, we should have a third one right there and another one right here. So it should be better if this was pixels of 5, but we have one estimate there, second estimate there, and one there. So if there were more pixels in between this, then we can just linearly estimate the values between our different our different normalized cross correlation estimates. So we can we do a couple different actual calculations, then we estimate the values in between them to kind of increase the speed of the processing, basically.
And for the spline-based interpolant, how well do the absolute correlation values trend as a function of the amount of strain that you induced? Did you see a decrease in peak correlation as you further and further strain the material, or were you always able to achieve good correlation independent of the absolute strain applied?
That's a good question. I don't think I have data on that could answer that question. My sense that intuitively, I feel like it might be strain dependent. If you have extreme strains, that you probably would get more error in there. But we haven't looked at that.
Yep, I'd agree with your intuition.
Yeah.
And if we now go back to looking at the realistic application of a clinical problem, if you have these strains induced and you have actually a necrotic core or a lipid core that's somewhat fluid-like, do you expect appreciable decorrelation as that fluid moves around such that the speckle pattern you're looking for actually now has changed and you can't find it as it is strained more?
Right. Yeah, that's a great question. It is, since we're doing our cross-correlation on the envelope signal, it's absolutely dependent on the image quality there. One could maybe potentially do more phase-based, do it on the RF signal, and it might be less dependent than on how the echo-lucent composition of the plaque is. So I think our algorithm probably is, to an extent, dependent on the echogenicity of these lipid areas, I would say. But it probably would make more sense in the future to go over to an algorithm that's based on RF, I think.
Further down that track, how small do you think your lesions could actually be? How small of a region of plaque could you actually characterize in this sort of way, both from the perspective of enough data to actually do the pattern matching, but also from the standpoint of as it's strained, if it's too small, it's going to potentially thin out and somewhat disappear on you.
Okay. So we have some data on that. When we were doing the patient study, we were able to measure plaques that had a diameter, a minimum diameter around 1.5 centimeters. And I think you can probably go a little smaller if you decrease your kernel size. But of course, when you decrease your kernel size, it's more difficult to track it. But for our algorithm, we found kind of a limitation around 1.5 centimeters. Now, if you switch to a RF-based algorithm, maybe it's more phase is more sensitive, so it might have the potential to improve the resolution further and measure even smaller plaques, I think.
Right now, what's the processing time to do all of this?
This is not real time at all. This is, we gather our data set and we do all our post-processing offline. It probably takes, I don't know, 10, 15 minutes maybe per patient, something like that. Not horrible, but I think if you wrote real code and implemented it in software, there are more or less real-time strain algorithms already in clinical machines, so I think that can be overcome.
How much is the clinician dependent on determining the region of interest to actually characterize? And would that be a first-order source of variability potentially?
Absolutely. So there's still going to be expertise required to use this algorithm. It's not going to be a system that anyone can use and obtain the right values. So you have to know where the borders of the plaque are, so you don't measure outside of the borders and outside of the arterial wall. And for me personally, I think that was difficult doing it on my own, and that's why we had the physicians outline the borders of the plaque so we wouldn't go beyond those distances. So I think, yeah, it has to be an expert physician with many years of experience to understand what regions he can measure in.
And just to give the audience some perspective, the amount of rigor in the literature for people to actually do validation work for techniques like this is actually typically quite lacking. So it's very refreshing actually to see so much effort dedicated to some sort of third-party external validation, as this did with an external measure also. So tremendous credit to you for undertaking that. Most people are scared to do that because of how poorly it will agree.
Right.
So that was actually really refreshing to see. The one last thing I was going to harp on study one before moving on was your percent strain error for radial and longitudinal strains were in the same order of magnitude of each other, but the amount of applied strain in each dimension was quite different.
Right.
The radial strain is tens of percent. I think you have a slide on that you showed.
Right.
The radial strain was tens of percent for a few percent error, and the longitudinal strain in your thesis is just a few single percent, but also a few percent error. And so you comment that they perform comparably, but the relative amount of strain is actually a very different percentage.
Right.
Do you have any comments there?
Right, so there's a lot less longitudinal strain in the body. Just to remind you, longitudinal strain is from left to right, radial strain is up and down. And as we saw in the videos, the plaque it primarily goes up and down as the pulse wave travels past it. Because we have much less longitudinal strain, I think we're much more subject to noise. We have a lower signal to noise ratio. So we're more subject to more error in this direction than in the radial direction, I believe. Yep.
Do you think a different tracking setup might help you? Because like you mentioned, you're effectively trying to track motion, one, that's not as strong, but two, the resolution in these orthogonal dimensions is quite different for ultrasound. So if you were to potentially have your dream setup and Matilda gave you infinite money to build whatever you wanted, what would you potentially throw at this technically to maybe overcome some of those challenges?
So that's a $1 million question. The main technical difficulty with this experiment is that we're not truly measuring in the same location. So we have 3 crystals here, 1, 2, and 3, and they're really measuring the motion. They use the law of cosine, so they're really measuring the motion here. And ideally, we want to place our red kernel or our red search area right there. The problem is you can see that it's a little darker underneath it. This is called shadowing, so that makes it difficult for us to follow the pattern. It makes it difficult for us to identify this speckle pattern from frame to frame. And that's probably one of the greatest weaknesses with doing this comparison, is that it's not a truly apples-to-apples comparison. So to overcome this, we would need either some type of crystals that don't provide shadowing, or some type of if we could somehow image so from different angles or something, so we don't get imaging underneath it. And I'm not sure if I have the answer, even if I had the infinite amount of money, that I could solve these 2 problems.
Yeah.
But I'd be welcome to suggestions if you have any.
No, the one you just alluded to actually probably would be to look at it at an angle. So effectively try to get the benefits of some of the axial resolution that you know you're way better at, and actually try to resolve the components of motion potentially a bit better. But as you mentioned, challenging in a complicated environment like this, because different angles will be susceptible to shadowing and corruption and things like that. So, great. I think we'd move on to study 2. This is way more into my expertise too in shear wave imaging. So the first big overview question I had for your shear wave analysis is you've placed a heavy emphasis on teasing apart the nuances due to Lamb mode propagation, which is, again, a commendable thing because it's a non-trivial analysis task. Why choose the Lamb mode as the primary source of dispersion over, let's say, viscosity or potentially what you eventually will assume in vivo is a confounder of anisotropy? Why is the Lamb mode kind of where you've latched onto?
Sure. I think the Lamb, an anti-symmetric Lamb wave is kind of nice because it's similar to Shear waves. So in wave propagation, we have really two types of waves. We have compressional waves, or we have transverse waves. So a Shear wave is a transverse wave, meaning that in the motion of direction, the wave is traveling up and down as it propagates in this direction. And a Lamb wave, an anti-symmetric Lamb wave, has a very similar shape. So I'm going to draw a plate here, an anti-symmetric wave in a plate. So it has a very similar shape as opposed to a symmetric Lamb wave, which looks like that. And because of these, I think, geometrical similarities, I think it's an appropriate model, even though we lack maybe the physical connection in our case that we're measuring. We're trying to measure stiffness in plaque. We'd want some type of either cylindrical geometry or even more complicated geometry to mimic the plaque geometry. But because this isn't available and this is the closest thing that we have, I think that it's, we're making do.
How important, so you're using a plate wave model to model dispersion, yet you went through all of the trouble of making cylinders instead of plates for your phantoms. Mm-hmm. Why go through all that trouble to make a more complicated phantom that was cylindrical, but then map it to a mathematical model that could have been a flat plate?
Right. I think in the end, the physical connection is important, right? That we're working with arteries, and to me, the study's about trying to mimic reality, not trying to validate a plate model. So that's kind of like secondary to accurately mimicking, as accurately as possible, the actual geometry of the carotid artery with a plaque in it.
Have you confirmed experimentally that you actually see an anti-symmetric mode? So you, for example, if you looked at your phantoms, you could look at the displacement at the top, proximal and distal surface, and actually see that they are moving in phase with each other. Has that actually been confirmed?
I don't think I've done it personally, no.
Moving to the same question I asked for study 1 with study 2, it looked like you jumped between systems a lot between the different studies, as I assume new hardware came online and new collaborations and new resources in that way. As I alluded to in my opening question about looking at heterogeneity of plaques and resolution of stiffness, what do you think would be the best transducer setup and tracking configuration to get the best stiffness resolution out of the shear wave techniques, and considerations like focal configuration, frequency you'd be looking at, and specifically the radiation force configuration versus the displacement estimation configuration?
Mm-hmm. I'm going to kind of answer this beyond my imaginary probe, if I wasn't constrained to physics. So let's see. Well, ideally, we'd probably want to increase the frequency that we're imaging at to get enhanced resolution to better track the shear wave. At the same time, we have to have a probe with wide bandwidth because we still want to push at a fairly low frequency so all the energy doesn't attenuate before we reach the arterial wall. So we'd want some type of transducer with a very wide bandwidth so we could push at higher frequencies. I don't have an exact number, but say 10 megahertz maybe. I don't know, we're pushing at 5 today. If we could double it, and if we image at 5. But if we could still push probably around where we're doing, or it might be even beneficial to try to push even lower to reduce the attenuation even more as it penetrates through the tissue.
Just so the audience understands, why does frequency matter with respect to penetration depth?
Right, so as you increase the frequency for ultrasound, you get better image resolution. But one downside is that the imaging depth decreases. They can't travel as far, and the tissue. So if we have a really high frequency, say 20 or 40 megahertz, we're maybe not going to reach the depths required for imaging the carotid artery.
So back then to the original thing, so you'd have a lower frequency for the radiation push to get it down. Higher tracking frequency buys you said improved resolution. What does that do to potentially the bias and jitter of the displacement estimate? Does it make a more accurate estimate? Does it reduce the variance in the estimate?
That's a good question. We haven't looked at that ourselves. With our first ultrasound machine, we had a fixed frequency, so we couldn't increase it. With the Verisonics, we can, but I don't think we haven't looked at that personally yet. So I'm not sure.
Yeah, and it's from personal experience, how it theoretically should improve and how it actually improves. For some context, there's mathematical derivations. The Kramer-Rao lower bound is one highly touted equation that's probably extensively overused to estimate, for example, jitter floors as a function of frequency and bandwidth and kernel size and all these things. But of course, it's a analytic theoretical framework to do this. The fact that you got such good results with actually using such a low tracking frequency was, again, quite impressive. So kudos there also. How do you think, so in your study 1, you took your phantoms and embedded them in a solid background. In study 2, you kept it in an all-water background.
Right.
What do you think are the differences in how the phantom responds with a solid background constraint versus a fluid? And specifically, how does that potentially influence the Lamb mode propagation you might see?
So in the first study, we surrounded it with a tissue, primarily because when we connected it to a pump, we get we get this pulse wave that travels through the phantom, but this wave bounces back and forth and causes reverberations. So the phantom's constantly moving. So the tissue was there to partially dampen this effect. For shear wave elastography, we don't. Our waves are very small. They're on the order of micrometers, very tiny waves. So they're not going to cause, and they also attenuate very quickly. So they're not going to cause these reverberations. So we weren't required to have a stiff tissue around it in order to conduct our measurements. If we think about study 4 and compare to study 2, in study 4 we did have a gelatin around our phantom and did our shear wave measurements as opposed to the water surrounding study 2. And I don't think I've really compared the variance between the two studies to see how it changes. But to an extent, the arteries kind of act as a waveguide to an extent. So I think the surrounding tissue, if it does anything, it should probably acts more as an attenuator for the push, making it more difficult to achieve larger pushes when it's there versus the surrounding water.
I agree. A couple of your studies you impose, starting in study 2, impose some big assumptions to go between shear wave speed and modulus. One of my big questions is, why impose those assumptions to give a modulus? Why not potentially make your quantitative metric that you would report in a diagnostic system just be the direct speed that you measure? Why impose the extra layer of assumptions, some of which you know you violate?
Yep. That's a good question, and that kind of goes back to my one of the first questions that we were talking about, like what do the scientists want and what do the clinicians want? And I think as scientists we want more scientific information and we want stiffnesses. And maybe that's not useful for clinicians, and it might be better to just end at the wave speed, like a group velocity measurement. And going forward, I think if I was going to actually implement this, my feeling is that it probably is better to end there for a couple of reasons. 2 main reasons. Like you said, we violate certain assumptions. And 2, that information is maybe just not clinically relevant to them. They might just be fine with wave speeds and comparing the wave speed in a vulnerable plaque versus a stable plaque. So I think you have a good point that maybe that's the way to go in the future.
And just for context, shear wave speed has probably the most traction in characterizing liver fibrosis. And in the field of liver fibrosis is actually a teeny bit of a crisis. There's probably 9, 10 commercial systems, and they all report different metrics. Some report shear stiffness, some report Young's modulus, some report shear wave speed, and clinicians have a difficult time knowing what's what for what should be the same thing. Do modulus and shear wave speed linearly trend with each other? Or is there a nonlinear relationship between them?
There's a nonlinear relationship for group velocity, right? Since it's the shear modulus is equal to the density of the shear wave speed, so we're squaring the shear wave speed, right?
Right, and so your insight is probably in the minority to the majority of the field, which loves to do statistical tests with one metric like a modulus and then just say, oh, it'd be the same for speed, when in fact they're nonlinearly related to each other. Another highlight there, of course, is that by looking at the speed, you potentially could actually augment some of the differences that you might have with respect to seeing a modulus difference when things might actually be closer together in speed because you don't have the quadratic amplification that you would have there. Let's see, further on in study 2, so you also tackled, in addition to the challenges of doing validation, you also did the challenges of taking noisy temporal data and trying to move it into the frequency domain, which is never well. And you actually had a really good slide on that.
Yep.
Your methodology slide for the K-space.
Yep.
So I mentioned before to everyone that it's about a slide a month. Usually getting this part of it working, this one slide probably took more like 6 months.
Yeah. Like that.
A nonlinear distribution of time to slide. So I was wondering if you could discuss some of the actual challenges of trying to get an accurate Fourier space representation of your raw waveform, and also maybe a bit of a clarification here. A lot of the displacement waveforms that you show in your thesis look biphasic. They have a positive and a negative phase to them, which is more traditional of a velocity profile. So I was wondering if you could comment on the nomenclature of displacement versus velocity, and then kind of the challenges of working with those data to move them into the Fourier domain.
Okay. So yeah, answering the last question first, our displacement maps. So we discussed this the past couple of days, and what we're actually measuring is the displacement from frame to frame, not the cumulative displacement over time. And that's, okay, we don't have any labels on this color bar right here, but the red's positive values and blue's negative values. So this is a displacement from frame to frame, and that's why we see this biphasic response. And many groups refer to this as velocity, from what I understand. So it's not only the ultrasound industry that's measuring different things and comparing different things, it's also academia. We're measuring the same thing, just giving it different names. So that was the first question. What was the second question?
The challenges of working with those data to move them into the Fourier space. Specifically, you have a very limited window of space and time data that you're trying to convert over into this K-space representation, and you've gone through a lot of steps of thresholding and cutting off things in the sort.
Yeah, there's a lot of steps here. So there's a couple challenges right away after we have tracked our shear wave. You can kind of see here this little green-yellow line here. This is a reflection from the wave, a reflection coming off the wall or the plaque and bouncing back. And this can result in a lot of noise in our later processing. So what we do is we actually cut off the data right there to avoid that reflection. That's one of the challenges that we're doing. So we crop our data set to get rid of everything that we don't want, or we think we don't want in this stage, and move forward. The other challenges that we really face are once we get to our, let's see, it would be the phase velocity plots here. Sometimes, not in this example, but they can be very noisy, especially around low frequencies like this. And we're trying to find the maximum intensity, and then sometimes our algorithms don't track the maximum accurately. There can be like random maximum points down here. You can overcome this by cropping out those outliers so that your algorithm will track the maximum wave accurately. Those are a couple tricks that we do to make the processing easier.
What about considerations of how close to the radiation force excitation you get? So kind of a step just back
yeah.
into a different analogous space. If I was trying to estimate a speed a pitcher was throwing a baseball, I wouldn't necessarily want to take into account all the time the baseball was in the pitcher's hand.
Exactly.
I'd want to look at the ball once it was actually released and traveling.
Right.
A lot of your plots appear to include right at the excitation in the analysis. What are your thoughts on influence of that?
Right. So we probably start 2 millimeters away from the actual push location. But you're right, you can see part of that excitation there in red, which I think, I haven't really tried cropping this away, but it could be related to a lot of this low frequency noise that we're seeing.
Yeah, I think you might actually make your life way easier by getting rid of some of that initial energy. So shear waves, just like acoustic waves, will have a near field and a far field. And pretty much your 2 millimeters, I would guess, is right at that transition point, probably clipping a little bit. But it can be potentially to not have to have so many empirical steps for cleaning up the K space. You could potentially address where your domains start and stop by that sort of an analysis point.
Right. And it can become a little tricky too, because if you have a really fast traveling wave, like in hard plaques and at high pressures, and your frame rate can't quite keep up, then your wave is going to be really flat here. So it can become a little difficult in those cases to do that crop, I think.
So this is jumping ahead to something else you had mentioned for study 3, but it comes up well now. Given that you're kind of doing a slope estimate here, and you already alluded to in your presentation how important frame rate was, and you expand upon the bandwidth of the shear wave, for this study, what do you think your actual shear wave speed resolution was? What would be both the fastest shear wave speed you could see, and what would be kind of the resolution or precision of a wave estimate that you would trust?
Right. So there's a couple things to point out. And so the fastest shear waves are in the hard plaque phantoms in the plaque, in the stiff plaque. And notice that the standard deviation is much greater for these very high measurements compared to these lower measurements in the wall and the plaque. And that's largely due to that we don't have quite the wave is traveling so fast that ideally we'd want a higher frame rate to track this wave with. So we're kind of losing some information, and maybe not, in this study in particular, achieving the bandwidths that we need, which we saw in study 3, to get as accurate estimates as possible. So, and you can kind of see that here too. If we assume that this mechanical test is correct, we can see that we're, for the most part, overestimating, which kind of makes sense, which aligns with study 3 as well. Now I don't have the wave speeds on there here, so I can't quite, I'm not sure what to comment on the maximum wave speed. Yeah, maybe 5, 6 meters per second, just off the top of my head.
For getting into the bandwidth consideration, so you did a really thorough analysis starting to look at effectively how much spectral content you need in your shear wave to start to be able to resolve these structures. And your methodology studies touted effectively what at least appeared to in my reading meant that you were choosing empirically a upper half space for the data set. So the actual spectral range you were looking at would change based on the data coming through. Is there an opportunity potentially for consistency and standardization of measurement, kind of as we're getting to what makes it more clinically viable, to choose a discrete frequency phase velocity that you could always report that would be present both in the hard plaques and the soft plaques, so that you weren't potentially constantly shifting the spectral domain you were interrogating?
So I think that's kind of similar. The question is kind of similar to, you're talking about choosing a fixed lower frequency for the upper half bandwidth.
Where they would, overlap. So
right. And I think you could also fix the maximum bandwidth. So say you can measure 2,000 hertz, but you always limit it to 1,500 or 1,700. And in later studies, I did that. In study number 4, for instance, I think I limited the upper bandwidth to, it's probably 1,700. And that gives you that same lower frequency cutoff point, because I understand the question that it's shifting around the whole time, so you get some, you get some error in there in your estimates. Yeah, so I think you could either do what you're suggesting, fix the lower part, or, as I did, fix the upper part, and you'd obtain kind of similar results.
Do you have a good singleton frequency that would overlap well? Like if I chose 1,000, would 1,000 be energetic enough in both hard and soft plaques, such that you would always get an estimate in both?
Right. Well, in the soft plaques, the bandwidth was about 800 or 900 hertz in many cases. So in that case, that would be too high. Yeah, we could find a single frequency to compare, perhaps, but yeah, it depends a little bit on this. I think this in the hard plaque situation, the speed of the wave, because and here's my rationale. If I draw that curve. So frequency, and we have the wave speed there. So this is our dispersion curve. This will be pretty high frequency for, this is for hard plaque. And say we want to choose a frequency of like 600 hertz, so that it both overlaps for the dispersion curve for the hard plaque and the soft plaque. The problem is if we draw the dispersion curve for the soft one, if I find my red pen, so blue is the hard plaque, red will be, well, they're going to be a little different speeds like that. So this will be for the soft plaque. Now if we just choose a point like 600 hertz like that, the problem is that we're going to be on very different parts of the dispersion curve relative to each other. So we'll be kind of towards, potentially be towards where this soft plaque dispersion curve may potentially be plateauing, whereas we'll be at, we'll be further down the plaque curve, I think. So in that sense, I'm not sure if it is good to choose a single frequency. Like maybe it would be more fair to compare, you know, somewhere closer to the plateau of the hard plaque versus, since we're looking at kind of more of the plateau for the soft plaque. If you understand what I'm...
Sounds like a good thesis topic for a younger student.
Yeah, right.
But this is kind of the heart of the issue. You could imagine if you only had the blue curve and you looked at two frequencies that were far apart from each other, even though it's the same material and the same curve describing it, you would get two totally different phase velocities.
Mm-hmm.
And so the question is, if you're trying to compare two different media and you are separating them too much, how much are you seeing just a difference because of the Lamb mode, where on that curve you are, just as you're highlighting? Is that a fair way to compare and potentially distinguish pathology? Or are you going to be too much biased by the fact that you're just more sensitive to the different Lamb, where you are in the Lamb mode regime, closer to the plateau or more in the gradient? My sentiment from reading the work and seeing your bandwidths is just like you drew it, is that right now you'd be flirting with the upper end of one and too much more into the lower end of the other,
right,
which would make it challenging. And this is why I think this problem is way harder than what's done in the liver, because everything bunches together there, but potentially also a ripe opportunity for diagnostic potential, because if these two really do start to spread apart, you've got a really good mechanism of contrast now.
Yeah.
Over that of what like B mode would have, or the sort. So well described. I was going to jump over to study 3 now.
Yep.
So you then tackled another extremely difficult thing, which is to actually try to do this in real tissue. So the hits just kept on coming for you. First question I had here was when you changed pulse duration. So this is the first study where you really started to introduce different excitation durations, and that was a mechanism that you correlated to spectral content of your shear waves. So the first question was, did you actually maintain the same excitation voltage across all pulse durations, such that you were actually getting a lot more energy in the radiation force push when you went up to 700 versus 1, or did you scale to keep constant energy as you change the excitation duration? And does it matter?
Well, so the way it works is due to hardware limitations in the ultrasound machine that we used, I think you're limited to a push length either of, I think it's 200 or 300 microseconds. So for these longer push lengths, it's actually 2 consecutive pushes followed right after each other. And the question is, does the voltage fully reach the capacitors before we can do that second push? And it probably doesn't. We haven't looked if it does. So we probably don't have as much energy in that second push, is my intuition from my engineering background, but we haven't measured that.
And to tout your Back to the Future type references, first generation RFI system we brought to the hospital had a gigantic 0.1 farad capacitor soldered onto the power supply to avoid that, and patients looked at us and thought we were nuts. But exactly, that would be one of the concerns. What you have up on this slide is probably actually the one plot that actually confused me in the thesis. So this right-hand plot was one I was hoping you could describe a little more here. So the general trend that you showed was that as you increased push length, you saw a decrease in the spectral content of your shear waves. And if we look at your Lamb wave curves, for example, like the one you drew on the marker board here, we expect a drop in the phase velocity as we see lower frequency content. Yet your trends here show increasing shear modulus with, if I relabeled the x-axis, it would actually be decreasing frequency content. So those trends in my mind seem to oppose each other. So I'm giving you the disclaimer here. I think this is the hardest question I might ask. But why do those two trends actually seem to fight with each other, in that you have a decreasing spectral content, yet you're showing an increasing shear modulus?
Right. So you're right. So as we increase the push length, the bandwidth is decreasing, and we're basically getting less and less data points on our dispersion curve here. And I'm sure it has to be with something how we do the fit. Now, I haven't looked at the raw data in a while, so I can't remember, but it could potentially be due to, so what's happening is that when we do our fit, it'll be a black line here. It's it's higher than our data set, which is the blue or the red curve. So maybe if the data set could also be more noisy, so there may be like outliers, even though we have less bandwidth, which kind of boost up our curve fit, is one potential solution, I think, and which would give you a higher shear modulus estimate as the bandwidth decreases. So I think that's probably most likely, that it has something to do with how noisy the data is.
So your physical intuition, do you put all your chips on the table for that plot?
Well, there's another thing that we have to consider here that I didn't mention in the presentation. So the push length, sometimes a short push length might not create enough of displacement as well in the tissue. And then we don't have anything to track anyway, so it's not going to work. So we have to also have long enough push length to where we can get enough tissue displacement to track a shear wave. So that's the other thing that we're balancing here, I think.
So if you were to put an error bar on kind of the reconstructed modulus as a function of push length, would those error bars potentially weaken the trend because they would be large enough because of lower SNR at those shorter push lengths?
Yeah, I think they would most likely be larger at the longer push lengths, yeah.
Okay. So that could just be all lost in the reconstruction and very dependent on the fit of the data that you're getting.
Potentially, I have to go back and look at the errors to study this.
Well, and this brings up the other point again. You have reconstructed to modulus, which means that you're amplifying these differences that the speed might have because you're squaring them. And so again, and the noise then is also, the reconstructed error bar is also amplified. But that question's behind you, and that's by the hardest one, so don't worry. For these, again, these assumptions here now of the Lamb wave, you've got these much more complex shapes in play. You've got potentially arteries now that have variable thickness as a function of the lateral propagation domain that you're looking at. Did you want to actively take into account varying thickness somehow with the Lamb wave model, or what are your considerations if you had 5 more years to dedicate to the project? How would you refine the technique to take into account now this heterogeneity, now that you're not working with a phantom?
Right. So, if you look at these real arteries, as arteries travel through the body, they become more narrow and narrow. What we're talking about is that the artery at this end has a much thicker wall thickness than even at 10 centimeters away from it. It's thinner. So what we did when we grabbed our ultrasound images, I don't think I have a picture of it here, but we measured the thickness at 3 different points, on the left side, in the middle, and the right side, and averaged the 3. And we did this for a variety of pressures to account, because the wall thickness changes as the artery becomes stiffer and stiffer, the thickness typically decreases. So that's how we took the wall thickness into account in our studies. Now, if I was going to continue with this in the future, I think I would, clinically, I think group velocity is the way to go. So I don't think I would worry about the thickness, since it's just dependent for the phase velocity. But I would focus more of my efforts trying to just do a group velocity study on a big population of different types of plaques and see if we can just, based on the average velocity, determine the different types of plaques.
How much of a thickness difference do you think you'd need to actually experience to have that skew the group velocity? Like, if it is truly a propagating Lamb mode and you're just lumping all the energy together, but you saw large-scale thickness changes, how big would that need to be to influence the group velocity?
Well, if we're just talking about arteries, like in this case, it's not going to influence it, because the shear wave travels about 2 centimeters here, and the thickness varies so little, less than 0.1 millimeters, which is not going to affect the results. In a plaque, though, a plaque can vary in morphology and thickness quite a bit over if it's a 2 centimeter long plaque. And how will that affect the group velocity? Well, it definitely affects it to a certain extent. If we look at study number 4, where we have these simulated plaques. With varying thickness here, affects it a little bit, but it's tough to say if that's going to bias the results, so much that we can't use them. I think we really need more data on different types of vulnerable plaque to see how extreme the variations in wave speed are, to see if this amount of error is acceptable.
Do you think, if you're starting to transition now to making this a clinically viable tool, if you were brought in as the specialist, cardiologist says they have a plaque, I want you to characterize it, do you think your recommended procedure, based on your experience, would be to put the excitation in the middle of the plaque and watch shear waves propagate that way, get to the outside of the plaque and try to couple shear waves in, or maybe try to do some sort of a relative estimate to see, characterize that pathology?
It partially depends on the size of the plaque, of course. If it's a real big plaque, if the shear wave can travel through the entire plaque, if I can place it outside the plaque and travel through the entire plaque, I'd go that way. But if it's a long plaque and I have to place it in the middle to measure the entire plaque or different regions, then that would be my recommendation to do so. I think the other thing that you have to think about, we're doing all the measurements in long axis images right now, and I think we need to also be doing cross-sectional measurements as well, since we could be missing vulnerable regions of the plaque. It could be out of plane, basically.
Oh, great, you opened that can of worms now. So how well centered right now do you think your technique needs to be in terms of having kind of symmetric plaque distribution in the elevation dimension for how your speed is affected in what you're reconstructing? So if you're obliquely catching the lesion, or if you're catching the edge of a lesion, if you were looking in cross-section, how much would that potentially be biasing you? And I know it's conjecture here, but do you have concern potentially that you could really mischaracterize a plaque if you're not hitting the center of the lesion itself?
Yeah, that's a good point. If we don't hit like a necrotic or lipid region of the plaque, and it's surrounded, the sides are surrounded by fibrous or calcified tissue, then you have a good point. We could be missing it. But I think by doing a combination of the two, longitudinal and cross-sectional, you can image most of the plaque, kind of semi, and eventually maybe we can use 3D probes to do 3D shear wave measurements on plaques eventually in the future. So
Another thesis project.
yep.
Oh, and just to contrast, so other imaging screening modalities, so you're not proposing this to be a screening method. This would be more of a characterization method for a known identified plaque. Is that correct?
Right. So I guess you still would do a first level B-mode screening to look for plaques. Once you found them, then you would use shear wave on them, for instance.
If you had calcifications in a plaque, to me that would potentially introduce some of the same challenges you had as in your first study when you had the beads in place.
Yeah.
What would be your recommended procedure, or what sort of artifacts would you expect from calcifications, and how would you work around those?
Right. So whenever you have calcifications, you should be getting some shadowing underneath them. What's different with the shear wave measurements compared to the speckle tracking is that we do measurements on the RF signal. So that that helps compared to doing it on envelope-based motion tracking. It's hard for me to know without seeing real calcified plaques and trying to do shear wave measurements on them to answer how big of an effect they will have on them. If it's, I don't think I can say today if it's not possible or possible, but we'll have to wait and see.
Okay. Now we're going to move into study 4 a little bit. So study 4, you yet again up the ante in trying to compare two things that aren't necessarily comparable, which is very bold.
Yeah.
I was wondering if you could comment actually first in pulse wave imaging. Their formula to reconstruct to a modulus seems even more egregious than what the shear wave community does to try to reconstruct to modulus. Can you comment a bit more in depth on right now all of the assumptions they try to make to move to a modulus estimate, and what in your opinion is violated in that reconstruction process?
Sure. So they use an equation called the Moenz-Korteweg equation, which takes you to the Young's modulus. The Young's modulus in homogeneous type tissues, it's simply 3 times shear modulus. I don't have the equation for it right here, but the Moenz-Korteweg equation, it takes into account the radius of the vessel, the wall thickness, the density of the blood, and the wave speed, of course. And there's a couple reasons why it doesn't work. For one, it doesn't take into account the wall, the dynamic wall movement, or how the wall thickness becomes thinner throughout the cardiac cycle. I think that's one problem. It doesn't also take into account as the radius changes, as the pulse wave travels past the point of measurement. Those are 2 major problems with it. It also, I think it assumes an infinitely long tube, which our arteries are not. So I think, off the top of my head, I think those are 3 of the main problems with it. I think there are more as well.
And is it clinically accepted to report the modulus instead of just the velocity?
I think clinically they report speeds. Yeah.
Speeds.
Yeah, velocities.
Okay.
Yeah, that's, once again, I think a scientist wants to know the modulus, and clinicians don't care.
So do you think that the pulse wave modulus, or whatever they're reconstructing, we'll put it in quotes, E, and the properties you're characterizing in terms of a shear modulus with shear wave speed, are those actually the same mechanical properties in a localized plaque estimate? One, from my perspective, one appears to be kind of a global impression of how the overall vessel accommodates this pulsatile flow profile coming through, and the other one is a much more discrete, localized estimate of a very small material property.
Yeah, no, I agree, and it's even more difficult to use the Mohns-Cordigo equation on a plaque compared to an artery, and it's even more invalid.
So the fact that, and I think you mentioned this, the fact that your speeds even came within the same order of magnitude of each other, happy coincidence?
Yeah, for the wall, like I briefly mentioned during the presentation, this is somewhat of a random result because the pulse wave speed is very related to the ratio between the lumen diameter and the wall thickness. So I think if we simply were to take the same phantom and just change the radius of the lumen, that we would get a very different result here for the wall measurement.
Just catching myself here. I have a plot that you didn't show in your presentation, but I think everyone has a paper copy. Page 5 of study 4, figure 2, shows a very similar representation of kind of your analysis you did in this study to the K-space analysis from the previous study. And in the K-space analysis of figure C, there's a lot of rippling energy present.
Right.
That wasn't the same characteristic K-space you showed in your earlier studies. I was wondering if you could comment on what that rippling was due to, and mainly because I think it then rears its head in what looks like slightly more complex morphology of your actual phase speed estimates in the subsequent plots in the paper. So again, it's figure 2C of study 4. Comments about why the K-space looks a bit different. I mean, it's actually quite clean.
Yeah.
Very clean K-space, but now you're actually probably seeing more influences of some other factors at play.
I'm not 100% sure what the ripples are, if they're due to noise in the displacement plot or if they are related to higher order modes of the traveling wave. So I don't.
They look very symmetric to me. Would you agree that kind of the bands across the main lobe are very symmetric? From my impression, they sort of look like a sync wave.
Okay.
And part of me is wondering if it's related to the finite rect windows that you have of space and time. Effectively, the convolution of that rect window will, at no point in your Fourier transforms did you actually round the windows off, right? There's no weighting to kind of decrease the severity of it, just gets chopped off in space and time.
Yeah, I don't believe so.
I think the sharp spatial and temporal transitions actually lead to a rippling in the frequency space.
Okay.
And you're potentially seeing effects of that there. It's remarkable how clean the data are. So I think all of this got smeared out in the earlier studies and was preserved here in what you might see. The other thing I was going to point out in figure, I think it was figure, the difference between figure 2 and figure 3 in this study was the frequency ranges that you looked at for the two plots. So for example, in figure 2D, you're showing shear wave elasticity metrics estimated from 800 to 1600 hertz.
Right.
And then in figure 3, it's pretty much a completely non-overlapping spectral content. It's from 300 to 700 hertz.
Yeah.
Did you want to comment on kind of why the big discrepancy there in kind of the spectral regions of what you were looking at? Is the phantom not a good representation of?
No, so it's very difficult to get the shear wave to propagate in these very soft plaque phantoms, which limits the bandwidth in the frequency domain. You can even see that in the second study that the bandwidth for the soft plaques is much smaller than the hard plaques. And I think that the PVA is fairly viscous when we make these soft plaques. So PVA becomes stiffer when you freeze it over time. We only freeze it one time for these soft plaques, and it's if you touch it and play around with it, it's a little bit like honey. It's very like slimy. So I think because of that viscosity, that can have an effect on limiting the bandwidth in that case. So I think that's why we see those differences in frequency.
So this could get back to what we were plotting before of these data would support that it would not be practical to have a single frequency at which you would estimate phase velocity between different types of stiffness, because the spectral energy just wouldn't overlap at all from that. How would you tackle, for again, the next generation student? You've highlighted that all these techniques have lots of assumptions in play. Another common way to approach these complex problems is to introduce inverse numerical models that kind of map out material distributions and the sort. Do you think there's any role for bringing in, for example, inverse finite element methods or more complicated higher order processing? Or do you think that further complicates a problem that divorces it more from what would be actually clinically useful?
Right, that's a good question. Yeah, I think that's one of those things that we are interested in as scientists again, but yeah, in the real world, I'm just not sure if it's clinically useful. So in my experience, I think it's better just to try to do a pilot study fairly quickly in clinics and see what the initial results say, and based off of those results, then decide if, okay, do we need more advanced modeling or analysis techniques, or is this good enough? So I think that's how I would approach it, because I think in the end it's all about whatever physicians want and trying to improve the diagnosis for the patient, not to try to get the exact shear modulus or stiffness.
Looking then forward, the technique, let's say, gets completely validated. You have your pie-in-the-sky version of it. It works. What are the different treatment options available to these patients if they actually get stiffness estimates that say, okay, this is more vulnerable? What is that going to trigger in the cascade of what someone might actually do? And is there a role for longitudinal monitoring of potentially intermediate form plaques? And do you see this technology having a role in maybe not intervening, but watching and waiting?
Okay. Yeah, so currently patients undergo endarterectomies or angioplasties. There's a new technique called stent retrievers, which is kind of like a plunger in a way. You put a stent through a plaque, expand the wire mesh, attaches to the plaque, and you pull it out via catheter. From what I've read, that seems to be getting this community excited, this group of surgeons excited. I think our technique can be, okay, it's good to identify the vulnerable plaques, but it can also be a very good monitoring tool. I think one of its strengths is that it can monitor plaque progression over time. So I see it being used for that, to monitor patients on a continual basis. Maybe catch them at a fairly early stage, hopefully at an early screening, while it's still a very small plaque, can prescribe them things like either medication or exercise and healthier diet, and hopefully limit the plaque growth over time. So this will allow you to do that and look at the plaque composition over time, hopefully.
Continuing down that path, let's say you determine you have a patient who you want to longitudinally monitor, and now you're the clinician performing this exam every 3 months, 6 months. How important do you think it is, and what's the influence, for example, of having your artery, every repeated measurement, perfectly parallel to the transducer face, such that you get wave propagation as orthogonally as possible?
Right.
Now toward what makes this actually clinically feasible to do this technique? Is that a type of confounder you'd be worried about?
Well, in our algorithm, we track across a straight line, but you can track over curved surfaces. The pulse wave algorithm, for instance, tracks over a curved line. And so I don't think that's a limitation, but that's something that I think you want to try to develop before you do that clinical study, because in most cases, yeah, the artery's not straight. It's always at an angle. A plaque's always at an angle too. So,
does putting it at an angle relative to your insonification with the radiation force challenge the Lamb wave assumptions at all? If you're kind of exciting it at an oblique angle relative to the top and bottom boundaries? I didn't prepare that question, but this one just kind of presented itself.
Yeah.
Specifically putting it into that antisymmetric mode, right? When you look at the antisymmetric mode, you could say, okay, well, I'm pushing on the top surface also, I'm pushing on the bottom surface and kind of moving the whole thing down.
Right.
Now if I hit it at an angle, am I potentially going to excite more complicated modes? Is that another student?
Yeah. Maybe potentially. I'm not sure how the angle affects the composition of the wave as it travels through.
I mean, you've developed an extremely robust phantom model. And, what easily can happen is you get the excitement of moving it clinically, and then some of kind of the first order studies could still be expanded upon by other students in the sort. It seems like a rich opportunity for me to take your existing models and, for example, do a controlled experiment as you tip it to see what biases are introduced if you didn't account for it. Does 1 degree matter? Does 5 degrees matter? Mainly from the clinical reality of a clinician trying to do this on a semi-fixed position, neck, handheld. What are the things that how close do they have to be to see whether they can get a repeatable measurement or not?
Right, yeah, and I think that's a good next step experiment to do in a lab setup, kind of controlled, and study the maximum angle that you can have and still obtain accurate results.
Since we've gone through the study specifically, I was going to regress back and just ask a few more general questions technically, and so a little more of a deep breath here.
Yep.
So if you've got these necrotic fluid-filled lipid pools in these plaques, fluids traditionally, or not traditionally, physically do not support shear. So is there a challenge of these fluids not supporting shear wave propagation, and you effectively don't see anything when you have a truly fluid-filled plaque or core of a plaque?
Okay. I haven't seen a ton of real plaques, but from my understanding, I don't think they're truly 100% fluid filled. I think it's kind of I don't know what to call it, like a slush, fatty slush, and maybe I'm wrong there, but if it was truly fluid filled, you're right. The shear waves don't propagate in liquids. But I guess that's something we have to look at as well.
Could you expand your plaque phantom model, quote unquote, easily to include a core where you could actually test this?
We haven't tried cores with fluids, but I have been attempting heterogeneous plaque models as well. We tried it in the pulse wave study. We had results for only one plaque phantom, but we felt that it wasn't enough data to draw conclusive results from. But in the construction technique, it could potentially be done to make a fluid-filled one if you could somehow seal it off and maybe use super glue or something to seal off that cavity.
And a lot of your studies you presented, you had kind of two categories of plaques, hard and soft. The case of the vulnerable plaque could have potentially a stiff fibrous cap and a soft core. So you would have potentially both hard and soft. And you've advocated for bias towards using a group speed measurement. How do you see those two compete with each other in terms of what you would get as a overall mechanical assessment of something that would have a stiffer outside and a softer interior in that vulnerable case?
Right. So when we do our shear wave measurements, we don't do the measurement in the entire plaque. We do it over, right now we do it over a couple lateral lines. Exactly. So we do our measurements between these two white lines. So if we had a thin fibrous cap here, it kind of looks like we do it and have one of those in our models even. it doesn't affect our region of analysis for the propagation of the group velocity. So I think you can stick away from that. And given that we don't get a ton of shadowing and all those problems, then I still think we can measure the lipid or necrotic core of the plaque.
So in contrast, if you looked at something like pulse wave, which is then kind of just going through, it's seeing a net effect of what potentially the vessel and the plaque would impose upon that localized velocity. So getting back to one of my first questions then, even though you like group velocity, it sounds like you like group velocity, but over a very small reconstruction domain that would allow you to effectively point characterize various aspects of the plaque itself. So if you had a large plaque like you've put up here, do you think you'd have a recommendation then for clinical deployment of actually moving that yellow line to multiple points throughout the plaque to get measurements across it? And would you want to combine those sorts of things again to get a singleton quantitative value for the plaque? Or would you actually potentially see value in looking at trends across the plaque length?
I kind of like this color map here where they've this is a color map where they've indicated different speeds of the shear wave. The machine does this by default. Yeah, I think we can measure at multiple points in the plaque if we have a plaque that's that large size. These phantoms, these are unrealistically large plaques. These are about 4 centimeters in length. You typically won't see anything that large in vivo, so you won't have to make multiple measurements. But yeah, I think you could create group velocity maps kind of like this if you wanted to, or you, like you suggested, we could do multiple pushes and try to average them as well. I think I'm not sure quite what would be best clinically. Of course, it's interesting to look at different speeds throughout the plaque, but I don't know, if we just want to compare averages to each other, then that's the way we should go with that. So I think that's something you have to kind of play with and ask what the clinicians what they want, what they're interested in, because I think we can provide both.
Do you believe the commercial provided measurements relative to what you reconstructed? You have them superimposed here. That wasn't really a point of analysis in your study.
No, I think we compared to the machine values a little bit in study number 2. There's a table there. Let's see.
Because the machine values are not assuming Lamb wave modes or anything like that. No, exactly. So I think in study 2, we were really interested in finding the exact shear modulus, doing phase velocity analysis, and right, the machine can't do anything like that. It just measures the group velocity, and we don't even really know how they do it, so I can't comment, what they're doing. But I think I have to look at that table again to see if we got similar values. Last question I was going to wrap up with here is kind of then another bigger picture question is, what is from your experience, how does the radiation force distribution of the excitation need to fully encompass the thickness of the layer or not in terms of getting an accurate excitation to give a true antisymmetric wave? So for example, if this was soft tissue above it, and your focus was maybe really close to the proximal wall, and you had a gradient of push through the thickness of that layer and into the plaque, is that going to skew what you would see? What would be your recommended kind of approach of where you'd want to focus? How deep of a depth of field do you need for the push, and does it need to be uniform in kind of spatial extent?
Right. So I think ideally we'd want to push in the middle of the plaque or off in the middle of the wall to the side. If we push off to the side here, now we haven't really tried that experiment, just doing a single push close to either of the boundaries and seeing how the wave travels. But my tuition is that we're going to lose a lot of the energy to the surrounding tissue, so I think the wave will be much weaker and more difficult to track. So I think that's going to be the main disadvantage.
And would it violate the Lamb wave propagation mode more? if you didn't get a push throughout the full thickness of the vessel wall? Would it look antisymmetric?
That's a good question.
I don't necessarily know the answer either.
Yeah,
You're the expert in this now, so.
I don't think I can say yes or no either. Yeah, I'm gonna have to pass on that one.
Yeah, no, I think that's a tricky one, especially when you've got the soft tissue above it. Because with soft tissue present, you'll, like you mentioned before, get that attenuation. So you're going to be effectively weakening the ideal focusing of it and distributing that push to a much greater region above the vessel.
Mm-hmm.
I think it makes it more challenging. And I said that was my last question. Let me ask one more. You dedicated a lot of time, we mentioned before, to the pulse duration as a mechanism of changing the frequency content of the shear waves. How would potentially changing something like the F number or the frequency of the radiation force excitation change the spectral content of the shear waves? Effectively, if you had a tighter focus to the radiation force and we're pushing over a much smaller area, how would that influence the shear wave spectral content versus like a very low frequency broad push?
I think if we have a very focused push in a very small area, my intuition is that we're going to get more displacement. It'll be easier to track the shear wave, and because we get some more displacement, maybe we'll have a wider frequency content. That's my intuition. Yeah.
Yeah, I totally agree with that. So I think that's a PhD-worthy intuition type comment. So in general, I think what you modulated with temporal duration is actually the harder way to modulate bandwidth. Our experience is typically tighter focusing and changing frequency spatially is actually an easier way to get after it. So again, you went after the harder task.
Okay.
So that wraps up all my focused questioning. So Erik, job well done on some thorough questioning there.
Thank you very much.
Thank you. And then it's the examination committee's turn to ask their questions. Could I invite you first, Rebecca?
Okay, that's the privilege of being a woman in the committee every time. Okay, congratulations and thank you for a brilliant examination, actually. And it was an honor to be invited and to read your thesis, which is of course too complex for a simple surgeon like myself. But I have some quite important, I think, general clinical questions. And I think it's really fun that you're trying to elaborate and develop our clinical tools to improve our care. I have some problems, however, when I read your thesis, because I understand that you're not a doctor, but there are some issues that you have to address when you think about carotid disease. And the first problem that is sort of general is what is actually the correlation, do you think, between stroke in the society and carotid disease? Do you have any impression of the correlation there?
Yeah, I've seen some data on that. So if we kind of start at a high level from cardiovascular diseases, stroke is approximately a third of cardiovascular diseases. Approximately, I've seen numbers anywhere from 15 to 30% of stroke is correlated with carotid artery disease. So
exactly. So it's a small number. I mean, in the whole picture, it's not the most important correlation for stroke. So stroke is more dependent on hypertension, for example, or cardiac disease. But even so, it's a devastating disease when it occurs. So what I would like you to elaborate a little on is, when do we actually treat the patient? What is the sort of most important gatekeeper for being treated for carotid disease?
I'm not sure I understand the question. What do you mean by
Do we
gatekeeper?
treat a person? What's the
When
majority of patients that I actually operate carotids on? Why do I operate them?
Right. So it would be the patients that are at the highest risk for plaque rupture. So like I mentioned earlier, from my understanding, it's primarily diagnosed on the degree of stenosis, but there's also other factors that are taken into consideration, like morphology and echogenicity of the plaque as well.
Well, the true gatekeeper is actually symptoms. So my biggest problem with this is that the majority of patients that actually come in, they have a symptom of stroke. And that's the majority of the patients that come
Right.
to the hospitals with a stroke. And then we investigate them, and then 10% of them will have a carotid disease. So we will treat them with surgery. So doing these investigations are fun and nice and interesting, but the patient actually has a stroke, and that's actually what determines the
Right.
treatment. So when I want to use your investigations would rather be in a screening purpose
Right.
to investigate the population and see, okay, which of these patients would have a carotid. And then I would like to ask you, do you think in a 5-year period that any of these methods would be as good as just measuring the degree of stenosis that we do today with an ordinary duplex sonography?
Mhm. Yeah, I definitely think these techniques can be incorporated into screening. I think that, like we were talking about, the advantages of many of these techniques, specifically shear wave elastography, is that you can monitor the progression of plaque development over time. That's really the strength of that technique. So, in a sense, I think we can maybe we have to rethink the way we screen patients, start at earlier stages, so that we can try to stop the problem before it becomes too late. In a sense, like you said, it's too late if they already come in and have already had a stroke. So I think these techniques can be used to rethink the way that we screen patients, maybe at an earlier stage, and do change either the person's habit in terms of diet, start medicating the patient on blood thinners.
And one final question, and then I will let the guys here ask their questions. How much, or is it even possible to even use these methods on a bifurcated artery? I'm really troubled because everything here is just straight.
Right.
Straight pig aortas or straight, and it's not even circumferential. And I mean, the plaque, you never have just one lesion. You have a wall, and you have, in the diabetic patient, you would have a medial calcification, and in others you would have in the intima. And then it's not almost always a tandem lesion. And then it's in the internal artery and not in the commune artery. So how could you even use this velocity measurements in a bifurcated with some sort of meaningful summary?
Yep, that's a good question. So the reason why we do everything straight in cylindrical geometries is that's what's easy for us as engineers. It's easy to fabricate these things. It's much more difficult to fabricate a bifurcated experimental setup. So that's why we avoid that. We can use these techniques in the bifurcation, I believe. I think we can do Swede measurements there. We have done speckle tracking measurements in the bifurcation and in the internal carotid arteries as well. I think I showed an example of a patient with an internal carotid artery plaque in the beginning. So my answer is yes, I do believe that we can do this measurement in bifurcations, and we really just do this because it's easier for us to do it experimentally.
Well, that's going to be very interesting, and you're welcome to come and contact us. We treat 100 patients every year, so we can try it on some of our patients.
It sounds good.
Yeah, I also will say thank you for a very interesting discussion and interesting reading. You have evaluated 3 different methods and using phantoms and reference methods. Today and in the thesis you talk a lot of accuracy, but you don't talk so much about reproducibility and repeatability. Can you say something about that?
Right, that we can be consistently repeatable, but maybe we're not accurate. Is that what you're alluding to? That accuracy is not the same as reproducibility. Right, so I think we try to address both issues in different studies. I think we try to address accuracy, in, for instance, the mechanical testing study for shear wave, and in the first study for speckle tracking with sonomicrometry. And we talk more about repeatability in the third study when we look at the bandwidth versus the push length. I think that we show, there's limitations to the mechanical testing as well in the shear wave studies, but I think we show that we are fairly accurate compared to other forms of testing at least.
I also agree that you show that you're fairly accurate, but I don't see how. I'm interested in how and in numbers of methods. Which of our methods is easiest to do? Get same measurements.
Repeatability. I think shear wave is the easiest one has the best repeatability of all three techniques, I think.
In page 50, in your validation you use Porcine in the validation of shear wave measurements. And you said that it was a pity that you didn't use common carotid artery. Why do you think that was a disadvantage?
Why was it a disadvantage to use aorta?
Yeah.
Well, in this case, I think it was almost an advantage because it was very similar dimensions to the human carotid artery. These were very small pigs, so their carotid arteries were very small, too small to use.
No, actually, I think it was very good because in pigs, the common carotid artery very soon get muscular artery, and in common carotid artery and aorta in human is elastic artery, and so therefore I think it was a good choice. The introductions section in the doctoral thesis, I guess, is where you put everything your work in perspective. Elsewhere in the world, and I would like to discuss chapter 7 a little bit, page 21 and 23. What was your purpose with chapter 7?
Just gotta look at it real quick here. So this is the kind of an overview of how plaques are screened today, and I think I briefly talk about also other non-invasive ultrasound-based techniques, and briefly mention some other techniques like MRI and CT as well at the end of it.
I'm some technologies there, so I just wonder how made you choose your reference, and how did you do when you tried to find all the methods that is in your area?
Are you missing other ultrasound techniques or other techniques?
Yeah, both. I a little bit miss vitro histology, which has been a golden standard. I can agree that lots of people don't believe it anymore, but it has been an important method. I guess the new golden standard is laser spectroscopy. Maybe I missed it, but
okay.
I also missed a bit Christie Court work using plane wave in transversal direction.
Okay, yeah. I've mostly read his intravascular work.
And I also would like to discuss a little bit the first sentence in the last paragraph.
Sure.
Where you claim that other techniques have been attempted, including assessing the arterial strain ratio, attenuation coefficient, and scatter size to distinguish fibrous, calcified, and lipid ex vivo plaques, but no in vivo experiments have been performed. Is that entirely true?
There could be a chance that new studies have came out since I've read this, or that I've missed a study, perhaps.
But is Shear et al. 2009? You referenced to Shear et al. 2008. Until 2009, they're using scatter size in 10 in vivo plaque. And Yamada 2009, 40 subjects, where we test the use of statin and scatter size, and also work which are close to my heart, Earle et al. 2016, which was on 50 plaques, I think. Anyway, what would be the disadvantage and advantages with attenuation coefficient and scatter size versus motion measurement?
Well, attenuation coefficient, that could be very dependent on the ultrasound machine settings, I believe, potentially, and there could be a difference between from ultrasound to ultrasound machine, different models, I would think. Different scatter size. I'm not too familiar with that technique. Yeah, I don't think I'm familiar enough with that technique to highlight the difficulties with it. But compared to our wave-based measurements, you know, I think every technique has its advantages and disadvantages. No one's a silver bullet, you know. So if anything, I think I'm happy to see that a lot of different research is done on a lot of different types of techniques to characterize plaque.
I guess there is still questions whether you can use attenuation coefficient or scatter size. But one advantage those methods has compared to motion estimation is that I guess motion estimation you need to have good image quality over several carrier cycles or like that. Do you think we can overcome that problem with the
right? Yeah, I mean that's a big difference between speckle tracking and shear wave, for instance, that we measure over one or more cardiac cycles for speckle tracking, and you know, just a couple of milliseconds of data with shear wave elastography. So I think that's one big advantage that shear wave has. Speckle tracking, it's difficult in reality for patients to be motionless and hold their breath for a couple seconds to acquire data. So I think that's a major disadvantage with that technique.
Last question. You discuss it. You discuss it today, but I'm not. Anyway, the resolution of the three different methods. Can you say a little bit about that? Which method have the best resolution?
Okay. So if we're talking just in terms of measuring plaque size, like I said, speckle tracking, we can measure plaques that are about 1.5 centimeters in diameter. For shear wave, I played around a little bit with how small of a shear wave do we need to still get, you know, consistent measurements. That's around 1 centimeter or so. Pulse wave imaging, we did our measurements over 2 centimeters. It's a little trickier to answer for pulse wave because they have another technique called piecewise pulse wave imaging, where they do estimates on, you know, segments that are 2 to 4 millimeters in length. But that technique, I'm personally a little skeptical to go that small, because basically what you're doing is you're limiting your number of data points, and whenever you have less data, your linear fits are going to be more inaccurate. So I think there needs to be more work done on piecewise pulse wave estimation.
So how good resolution do we need to get a good measurement, allowed to be able to distinguish stable plaques?
Depends on the plaques come in all kinds of different shapes and sizes. So ideally you want to have as small as possible so you can deal with the small ones too. But yeah, the smaller the better.
Yep. Thank you.
Okay, first of all, I would also like to thank you to Matilda and the organizers to invite me here. It's been a very nice discussion to hear between the opponents and you, and also the other in the committee. First of all, I'd like to be a bit critical about the idea that you had that perhaps we should remove the fika, as you mentioned in your. So
I knew it was going to be controversial.
That's my starting point. And actually, I had, well, a lot of my questions has already been covered. One of them was about the sort of representativeness of the ROIs that you use for characterization. I mean, given that plaques in general are heterogeneous. But I think that's been covered quite extensively. But relating to that, and also what you just talked about, it would have been nice to see or hear your thoughts about the influence of the width of your ROI and estimation performance, basically.
Sure.
And in a way, I think you have in paper, you talked about that you need a high pulse repetition frequency for hard tissues because the proper speed will be much faster. So perhaps you could just reflect on the influence of ROI width.
Sure. Basically, the length that we're tracking the shear wave over. Yeah, so that's kind of what we were just talking a little bit about, Magnus, about comes down to the resolution. And we haven't conducted any formal experiments on it. It's more of just informally playing around with the algorithm and see how small you can go before your estimates seem unreasonable or they take off. And it looks like we can go down about as small as a centimeter with shear waves from my own personal experience. But if it is a large plaque and we have the ability to track the shear wave over a large area, I think it's advantageous to track it as far as we can, as long as it's within the tissue that we want to characterize.
So your guess is at least down to 1 centimeter would be okay. I'm going to jump a bit back and forth here, but so paper 1, you used previously developed Speckle tracking method. Why did you use that specific method? I guess in terms of Speckle tracking, there are
there's
a huge amount of different techniques.
Right. So it's kind of a continuation of a body of work that Matilda started on during her PhD and postdoc. So it was by starting on that, it allowed us to quickly move into kind of a patient study, which we were very interested in doing, rather than developing a brand new algorithm from scratch. It had already been validated in arterial setups and shown that it worked really good there. So we thought that was a good starting point to move forward.
Okay. And actually, a detail on that. I think in the thesis, or I'm not sure where I read it, but it said there was an equation how you calculate the 2D correlation. Cross-correlation. And it talked about RF. So is it based on RF data, or is it like BMO, the modulated data?
Yeah, that was a misprint. It was on the errata here.
Sorry.
It's just on the envelope detected signal, not on RF data.
So it's if you only have access to BMO data, then you can use this and you know the performance of it.
Exactly. So
okay, great. Okay, and then I had a question about noise. You talk about noise in different aspects throughout the papers, and that some parts in, I think, paper 2 and 3, when you are processing the case base, you say that you basically crop out a part of it, and then you say that you removed the noise.
Mm-hmm.
So did you remove all noise by doing that, or?
No. So if we look at this image, maybe I can explain this. So here's our case space, and we're trying to actually we do this crop in the phase velocity plot here, and we're trying to track the maximum intensity. Sometimes we get this noise down here. We don't really have too much of it in this image, but we can get these random, it's almost like popcorn noise. and that can throw off our maximum detection algorithm. So we just kind of like, we can manually just crop that out, or you can design algorithms that filter out, that manually just crop away the values in this region. That's one way that we overcome it. So we don't crop away all the noise. I mean, there's also some noise up here, but that's usually not a problem for us.
So you have noise throughout the whole data and not just in that region that you cropped?
Yeah, there's noise in other regions, but it doesn't affect our maximum intensity calculation.
No, it's just my point was just the term removed, because I think in paper 4 you talked more about you reduced the noise.
Okay.
So removed in as opposed to reduce.
Yeah.
That was the only. I understood. I think how you did it. Many interesting things and therefore a lot of questions, but perhaps I shouldn't have too many questions either. One thing I thought about was that you have quite extensive work on understanding how the bandwidth and length of the pushing wave trade-off influences your results. And then I just came to think about in standard imaging, you also have this problem with the bandwidth as opposed to the length of the pulse. And then sometimes you use like pulse coding, pulse-coded excitation to handle that, so you can decrease the energy and you can have a long bandwidth but still have the temporal resolution. Is that from a theoretical point of view? Because I understand that if you have a too short push, you won't be able to measure anything because you haven't really pushed anything.
Mm-hmm.
So from a theoretical point of view, would it be possible to implement some kind of pulse coding techniques to handle that issue?
I'm not that familiar with pulse coding, but is it just like repeated pulses, basically, more or less?
In a way, coding means that you basically amplitude. You use different amplitudes in a sort of coded manner of the push sequences, of the push sequence, which means that you can, when you then detect it, you can use specific detection. Okay, but perhaps you're not.
I'm not that familiar with that, but what I can say is that if we do pushes that are very close after each other, for instance, this is the pushing sequence from the Supersonic Explorer machine. They do 3 pushes right after each other, and they call it a supersonic push. Each push is 150 microseconds in length, but they're so close to each other that the length of the shear wave, the actual push length, you just add them together. So it sees it as a push length of 450 microseconds. So it depends how close to each other the pushes fall that will affect the bandwidth. And we do the same thing in the Verisonics machine, which Mark and I talked about. For the very long push lengths, the hardware can't generate those long pushes, so you actually have to do 2 pushes right after each other to achieve those longer push lengths.
And just one more, 2 more questions. Based on that image, I'm a bit surprised that there's no difference between the fluid and the tissue because the blue is the color-coded.
Right.
Velocity.
There shouldn't be any velocity there. So this is a color code that's coming off of the machine, their algorithm. And I obviously can't speak to what they're doing, but in theory there should be no shear wave propagating in the fluid. So this is some type of error in their algorithm.
So theoretically you could use it in a larger field of view perspective to actually segment the plaque as well? Because I'm thinking about the hypoechoic plaques are difficult to detect.
Potentially, maybe, kind of,
Potentially,
maybe depending on your algorithm design. I'm not sure if it would outperform other segmentation algorithms. I doubt it. It's my intuition.
Okay, so just one final thing. In another biomedical engineering application, or in many biomedical engineering applications where you use quite simple techniques, there's a saying, easy to use and easy to abuse. And this technique is not very easy to use. Does this mean that it's difficult to abuse or easy to abuse?
Yeah, the goal is to make it easy to use. I think it'll get there, but I think any research tool you're developing it is not easy to use. Maybe we like to impress each other with our what we can do mathematically and scientifically, but at the end of the day, what this company has done, and they have an easy-to-use tool. It's not always right, but I think the tools have to be ease of use is more important than technical super accuracy, maybe, if that makes sense.
Okay, thank you.
Yes.
Thank you. And then I'd like to ask if there is anyone in the audience who would like to ask a question to Erik. Elira, please.
I would like to ask you the first project that you would suggest to the next student and your best advice.
Excellent question.
Thank you. We didn't agree on this, by the way.
Yeah. No, I think I'd like to see future students move on with the Shear Wave project. I think it has a lot of potential. I think there are a couple of, we need to do a clinical study pretty fast, but I think there are some things we should try to accomplish first. Just like curve tracking is one. I think Mark had a real good suggestion of doing an angled study, angling the probe at various angles. So a couple small projects like that before you move on to a plaque study. I think it'd be easier to do an arterial stiffness clinical study first, and then if we can get that working good, then we should move on to a plaque study. Best advice, don't give up. The road is long. Yeah, no, I think you have to do it because you're really interested in it. You obviously don't do it for the money. But yeah, you have to be really passionate about what you do going into it.
Yeah, we have seen a lot of nice research here. And I'm a clinician, surgeon. So if you elaborate a little bit, how long do you think it takes till this could be in clinical use, as question number one? And also, today in bigger hospitals, ultrasound is very specialized to just a few people. So they are very skilled. And if it becomes a clinical tool, how long do you think it takes for it to spread?
Cool, good questions. So I think for this to be used clinically, looking at something like, I don't know, I usually look at the past to look towards the future. So if we go back, 10, 15 years in ultrasound, I don't think we could have thought that we would be accomplishing the things we're doing in clinical machines today. So that's why I'm fairly optimistic about this, that it actually will be used someday. I don't think it'll be used within 5 years, maybe within a 10 to 15 year horizon to get it to actually working good. I think that's realistic. You're right, ultrasound is a very specialized tool. It's still going to be a specialized tool with this. It's not going to be something that anyone can use, and you're still going to have to be an expert within the field. But the one advantage that this technique has is because ultrasound machines are used in so many clinics that it can spread worldwide fairly quickly, and I think it can be implemented on most ultrasound machines. So it has the potential compared to MRI or CT, big expensive machines, to spread much faster and be implemented clinically faster because you don't have to buy an expensive machine, just a relatively inexpensive machine.
Thank you. Any more questions? If that is not the case, this part of the dissertation defense is closed, and it's time for the committee to withdraw. But before that, I would just like to address you, Mark, once more. You are our visitor from the farthest country. You came all the way across the Atlantic to perform this important task. I know it's a lot of work to be an opponent, and you certainly demonstrated that you have put lots of efforts into your work. Thank you so much.
Thank you very much.
And for everyone else who is not going to the examination committee, there will be refreshments on the 9th floor in that direction. Thank you.
Yes. Thank you.